That will be correct.
Yeah.
Yes.
I am happy with that.
Last year also it was.
उसको चेंज तो कर ऑटो फोकस पे ऑटो फोकस पे
Every penny they count and then they carefully maneuver the money because
आ गया ना आदित्य आ गया
so because of that those careful expenditure patterns and the frugality. So cost of living was the moment
It's the same thing as they
started
like
growing
collecting.
left and right, the rental things have increased. And, in fact, I have heard even in Malleshwaram shops, they say, I'm not working in IT, you cannot put tomato this much price and
Yes, I can stand here.
because of IT guys you are increasing and that doesn't work for common man, that was the argument essentially.
Not an issue.
So,
And that's up to you.
and then it
Guys.
became vehicle dense because they got affordability and other things. So for a while it was convenient.
सही है अब इधर आ
Traffic jam became
एक बार बाहर
तो रहा है।
मतलब इधर नीचे आ Yup. You need to go out I guess. भाई वहाँ तक है आ रहा है बाहर ही जाना पड़ेगा
What's happening?
The camera is checking के लिए
It's tracking me. But he has a remote, right?
Go out.
Actually the thing
That's
is
the
the
question.
menu shows up on the stream also
Oh.
go out
तो क्या आएगा?
हम देगा of course
What does it do then?
चलो कैमरा.
Yeah, it's awesome.
yeah now it tracks
Oh, also the anchors also, you know.
But once it sets on him, it
Yeah, yeah.
Yeah.
The anchors will also go out, otherwise it will stay on the anchor.
yeah they will have to go out
Why can't they sit back?
no I mean
Go
for
out
some
once
time
and then they can
when
go
it
out.
starts refocusing on the other people then they can
Has a very wide range.
Oh,
Yeah.
okay.
it tracks till there
Like I tried going till here, it's tracking.
Yeah.
Can you restrict its range?
I'm not sure.
Now that call that admin guy.
it was the same problem last time
Oh, he's here. Okay, he will know.
But yes, an AI is too good.
no I was thinking is there something we can do
Now? Now I'm in Malleshwaram. I'm next to Mantri Mall. There is a Mantri apartment.
yes stream देखते हैं भाई दो
Living there. Adjacent
stream
to
देख
Mantri
लो
Mall.
So your home is like pretty close to Nara Hills.
No. There is office here in the 9th.
we have started streaming
I
it is
will-
not public it is unlisted
Based
There
upon
is in the 9th cross.
Presentation based, yeah.
I hope it is unlisted
This Sampige Road and next to Sampige Road. See, 9th cross is going all the way from the Malleshwaram post office all the way down.
First class.
Huh?
3 months first class.
Mantri Mall is in the first cross. He is in the 9th cross.
So roughly
Between exactly halfway between IISc and my place. Because IISc is kind of 18th cross. We should say. He is in the 9th cross. I am in the 0th cross. First cross is different. That's called the South End Road, connecting Rajaji Nagar and other parts.
Palak. My laptop is working fine.
So my, technically my address
Are you
is
using
Pawan City.
PowerPoint or are you using the Mac thingy?
Using the Mac thingy.
But number one,
It works on mine.
It works on mine, that's fine.
we are 400 apartments. Gated community. Actually, earlier there was one rice in It was called Wilson.
we cannot
walk
there
the
we catch
The rice mill was in the one half he constructed the mall, and in the another half he constructed the mall. We have a shared.
You expect me to read extra. You know what I am. Akshay is coming now.
Did you call him? Darshan?
I didn't know.
I think he's gone.
Probably for cricket. I don't think he'll pick up his phone. Do we need him for cricket? The first talk has like, we started 11:15, right?
First off at 10:30.
Nah,
We don't need
students.
players or
Yeah, but
Students-
later.
Your first talk, right?
No, Aditya.
What
No,
time?
sorry,
12:15.
Aditya's talk first. So during Aditya's talk, you can do it. And then during your talk, Aditya can do it.
Anyone from our batch or any junior?
I'll
By
do
the
it.
time
Like we are
session
there.
should come.
I'll do it.
Yeah.
Or
See,
you
You are doing nicely, I'm doing the pictures.
I'm also. If Pramya is not sitting here, I'll also be here. If both
Aditya
of.
is sitting there.
So if two people are here, I can go to the class. For Aditya.
Huh.
No, I'm scared. What is my first?
Hey, who are the
Then screw them,
Wait.
we'll do the presentation first.
yeah, bro?
He's coming.
Crazy.
People come. Who are the professors other than the
I
one?
think only Pandu, Chiru and Arindam are supposed to come today.
And yeah, Chiru will come in the afternoon.
In the afternoon.
What?
I don't think any prof is going to stay for student talks
Yeah,
for
I
now.
don't think so.
Professor
They're
Pandu
not
will stay, but I
Pandu
don't,
will
I don't
stay
believe.
both
I don't think
days.
anyone
Nah,
else.
bro. I thought they'll come like 10 a.m. They'll come and leave early. I thought. Like, everyone
Their
wants
talks
to.
are in the afternoon.
Yeah.
They will come for
I mean,
their
yeah,
talk. They might
lunch is
leave
done.
just after that.
First
The
visitor.
only thing that's possible is that hello, good morning, good morning. The only thing that's possible is that Arindam might stay for
Yes.
Chiru's talk.
Huh,
That's the
yes.
only possibility. That's the only thing that will happen.
Yeah, people will give talks and go. People have like Twitter and some students talk in between talks.
No,
Then
like,
he would have left.
no, I think Chiru might stay for like 15 minutes after this talk. It's not
Yeah,
really.
because
he
he's a
won't
little
leave
bit of
after.
a database prof. Like I mean, in the sense that he has had some.
Yeah.
How many external?
You should trouble him a little more.
We
Actually.
had like
How many external like
20 students from
They
BM.
didn't
I hope they are.
the you
Oh,
check.
yeah, that's what it is.
Going
You guys change the audio again and everything.
Go with that.
On. It's on now. Hello? It's on now. No problem. You can use that.
On behalf of Database, the IISc Undergraduate Computer Science Club, I am thrilled to invite you to DBD Fest 25, our annual festival of code, creativity, and curiosity. Founded by some of the first cohorts of IISc's BS research program, Database was initially a significant group of students with an interest in venturing outside the classroom, exploring algorithms, systems, and the complex world of data.
It has since become one of the most vibrant student-run tech collectives on campus, organizing workshops, hackathons, and talks that translate theory into practical innovation. Today's event upholds that tradition, gathering enthusiasts, innovators, and learners in celebration of the computing spirit that pervades our community. So sit back, plug in, and get ready to see the best of what. Now, we are truly honored to welcome Professor Pandurangan from the Kotak IISc AI-ML Centre, a distinguished researcher whose work spans cryptography, distributed computing, and secure algorithmic design. His contributions have totally shaped our understanding of privacy, efficiency, and has built our trust in large-scale systems. He has also been a great support to the database community in making today's event a great success. Today, he'll be speaking on a topic that's both elegant and deeply practical: proxy re-encryption. So with great enthusiasm, let's welcome Professor Pandurangan as he takes us into the mathematics and mechanisms behind proxy re-encryption and the future of trust in distributed intelligence. Over to you.
Okay, thank you. Thank you very much. It's a pleasure and honor. Normally, we will typically start the event with the prayers, right? But there is another form of prayer called expressing gratitude. So I'm going to do that. Thanks. Usually, word of thanks is coming at the end where everybody neglected our words. I hate that model. I want to start with thanking people who have really. First of all, thanks for the students who have shown the enthusiasm to organize this event. Year after year, a tradition was set up by the first batch of students, which is followed by just outside classroom enthusiastic reading has now swelled into an activity where a lot of research papers are read, wide range of topics are read and discussed, and then this forum is gaining strength and multi-dimension over a period of time. Thanks for the students for the enthusiasm and making sure that this kind of an event creates a lot of vibe in the community. That's more important. What's very important is that we have classes, courses, grades, marks, and other things. And in an institution like IISc, how far you are going way beyond the classroom. It's a center of learning. So graduation is an opportunity that is opened up, but your view should be in terms of focusing on learning. And this kind of events give an opportunity for you to explore way outside the classroom, various topics, and then you are doing amazingly interesting job. And let's have more of these kind of events so that you all gain strength. This is point one. And an event of this kind cannot be organized without the enthusiastic support from the departments. First of all, the KIAC Centre has given us the financial support for the event. And the head of the department of CSA, he has given the infrastructure like the seminar hall and every infrastructure over here. You can see the online connections and then the seminar hall and supporting staff. All of them and enabled to make this event a success. So I would like to place on record the thanks for all of them. There is always an unwavering support from the UG Dean and then the undergraduate department. IISc is predominantly known as a research scholars fort. When an UG program was started, a separate unit for UG learning and then issues addressing all of them, from graduation, from admission to the graduation. They separately set up a division for it, and then there are a dean, associate dean. They not only look into various aspects of the administrative things, infrastructure, facilities and other things. The care that they take towards the student and the program is amazing. As you might have perhaps seen at the introductory level, the welcoming meet and also during the admission process counseling time, the enthusiastic organization by the UG team inviting various faculty members to not only showcase IISc, to show how much they care about your education here. So I would like to thank all these people, KIAC Centre, its head, the UG division and its dean and associate dean, Computer Science Department, School of Automation, Computer Science and Automation Division, their head and the faculty members, and the faculty members who come to us for the presentation in the afternoon. I would like to thank every student as well who have taken effort and spent time to go outside the class hours and learn something and then share in these 2 days. Okay, so with this warm note of thanks, to start with, I will begin my discussion and presentation on proxy re-encryption. So I'm going to go over quickly various things. After all, what is encryption or decryption meant for? Just a common sense understanding. A would like to send a message M to B, but this communication channel, like internet or your whatever is the communication channel, whether even it is a telephone, it can be wiretapped. That means there is an adversary who can wiretap, or he is also known as eavesdropper, adversary, various terms are used. He has an access to the communication channel. Okay. Simple example, your ATM PIN number, which you feed in an ATM machine, the bank server. So A and B need not be even people. One could be ATM server and another could be a bank server. So a message goes, your PIN number. If it goes in plain, you are in trouble, right? The adversary will know that. That means there are certain information that should be securely communicated. So what is the way to do? Access is there, so you have to do encryption. Okay? So M must be converted into something else, and that is called the encryption algorithm. So encryption of M is C, and decryption of C must obtain M back. One issue here in the security world is the following. The encryption algorithm and decryption algorithm must work in tandem. That's one thing. Another thing is, whatever is encrypted, even if it is encrypted, if I could recover from C, because he is seeing C, it is not M that is sent, it is the C that is seen by him. From C, even without going through the decryption algorithm, if somebody can recover M, the whole purpose is lost. What is the purpose of encryption if that can be easily reversed by anybody? Therefore, it is important that it should not be reversible, but that point brings in additional mathematical issues. Okay, how do I ensure that if it is not reversible? Well, if it is not reversible, encryption is such a function that it can't be reversed, then how will B be able to reverse it? B should reverse it, right? So, there is an algorithm, decryption algorithm, which is helping to reverse, but this must be exclusively be done only by B and not by others. So that how do we bring in that exclusivity? In technical terms, that is called the security. Only the intended person must be able to reverse it and not others. That means he must have a unique ability that world doesn't have. Nobody else, attacker or no one else should have that. Okay? So that is enabled by a piece of information. Okay, because we are in the IT world, exclusive access is sometimes can be given physically like this. You have a lock, physical lock. You have a key, physical key, and the key you keep it with you. Then who can access? Only you, because you can only open the lock and then you can. So that's the lock and key paradigm is what is mentioned even here. We use that. Okay, we call that as a key. Only you get the access. So the key is nothing but an information. We call that as a secret key. So we have various crypto systems available. The crypto system that we are going to discuss in today's context is called the public key cryptography. Public key cryptography. Every user A has a pair of keys. Public key of A and secret key of A. Every user. So if there is a user B, he will have public key of B and secret key of B. Okay, every user will have this one pair. This is called a public key crypto system. They generate it. Okay, secret key only he should know. That is what is giving him the power of security and secrecy. Therefore, you can't delegate it. You cannot ask your friend to create a password for your Gmail account. That's a disaster, right? Only you have to do it. So there is a key generation algorithm for which you input some parameters and you generate your public key and your secret key. Everybody, whole lot of millions of people who are using cryptography, if they are using public key cryptography, they have to first use the key generation algorithm to generate their public key and secret key. Okay, public key and secret key are related. That is because public key is used for encryption. Okay, so now our encryption algorithm will be like this: public key of A and a message M, and that will generate the ciphertext C. Decryption algorithm will use secret key of A and C, and then it will recover M. Notice that secret key of A is not available to the world. It is known only to A. Therefore, this algorithm cannot be executed. Not all parameters are available for attacker or eavesdropper. And secret key, therefore, this can be executed only by A. And only A can recover whatever the message that is sent to A. Encrypted for A can be decrypted. Encryption can be done by anybody. Anyone would like to send a message to A. Okay. Therefore, the whole world can send a message to A. How will they send a message? They have to run the encryption algorithm. Therefore, encryption algorithm, decryption algorithm, all of them will be made public. People know what system you are using. The security of the system depends only on the security of the secret key, nothing else. The whole world knows that. This is the algorithm, this is the encryption mechanism you are using. This is the decryption algorithm you are going to run. That also attacker and the world, everybody knows. What they do not have is the secret key, whereas decryption algorithms execution requires two parameters. Attacker will get access to C because he is wiretapping and he may have the C, but without secret key, attacker will have difficulty, whereas owner of the key can comfortably execute this and then recover. This gives that exclusivity or secrecy or privacy. Only one person can do. The authenticated person or the person who is designated to do the job alone will be able to do. Others, theoretically, and we want ideally, others should not be able to do. So encryption function can really convert into something that is not reversible. But that should be reversible with the help of a secret key, which only the authorized person will possess. Okay? So this is the mechanism. So what do you mean by a crypto system is not secure? A crypto system is not secure even without this part. Although this is generated, somehow from C I am getting M through some attacking algorithm. I don't need actually your key. It has certain properties. Because of this certain properties, I know that if I search a little bit with these kind of things, then I will be able to get M and then I am getting M. If I could do that, then your system is broken. Why your system is broken? I am able to get M from C Even without decryption algorithm, I don't care. I'm an attacker. I don't have your secret key. Like if I am able to log into your Gmail account, even without your password, somehow I do something, and then the whole thing is compromised. There is no security, there is no privacy, and other things over here. Therefore, this should be made as hard as possible or impossible. Okay? It should be made impossible or infeasible. How to make certain things impossible? Mathematical impossibility. Okay? That is called the information theoretic security. We will make it impossible. No matter what you have, no matter what, whether you may have quantum computer, you may have God on your side, you can't do that. That is information theoretic security. Computational security is infeasible. It is possible. Only thing is, you have to do a lot of computation, and in order to do that computation, you may require 300 years. Yes, continuous computation. It's finite, but that finite number is so large that you are going to take 300 years to break it and then get this. Doesn't matter. I am willing to implement that kind of a system. If I have a guarantee that to break it and then to obtain the information it is going to take 300 years, I am willing to encrypt using that algorithm. I am not considering that as a break, because nobody is going to live for 300 years, and that value of the secret itself may not live that valuable for 300 years. Therefore, the whole point is computational infeasibility. From impossibility to infeasibility, the moment the researchers have turned into the modern cryptography is born. Okay? So what they will focus is on making things very hard, computationally infeasible for the adversary to discover this. So we are assuming that the adversary has an access to the ciphertext. From ciphertext, he doesn't have an access to secret key, and he has to obtain M. How to obtain? How can we frustrate that guy? How to make him work hard? If you have a system that is going to make him work a lot harder, that is a secure system. Technically, it is called a computationally secure system, but that is okay. Okay, let's not worry about that. Nitpick on that data. Okay. For information theoretic security is working on that. Okay. Information, multi-party computation and other things, they all worry about information theoretic security. Okay. So computational security is what you might have heard about in the common part of RSA encryption scheme, Elgamal encryption, like that, various things. Do this computation and then produce it. Do this. Well, when you do this, from this you will never be able to get it. Never means it will take enormous amount of time. That's what it means. Okay? So, how do we frustrate an adversary? There is one fundamental strategy, basic and simple strategy for it. Every cryptographer or anybody who is interested in cryptography must know about this particular fundamental technique. Okay? Very simple idea. No matter what supercomputer you have, there is no way you can use any algorithm. You have to go through only exhaustively search for things, and I make the search space very, very large, much, much larger. For example, if you have a computer that can do trillions and trillions of operations in 1 second, even if I have some, let's say 10 power 80 computation is to be done, even if you have such a computer, it is going to take thousands of years to complete. That means if I have a very large search space, and in order to break, in order to find, you have to go through that search space, and there is no option. You can only guess, but then you will fail. Search space is very large. Then it's going to work in your favor. This is a core idea. This core idea, how do I mathematically implement and write a program and then do this? Here is a very simple technique. Okay. So, if you have heard this example before, because I have mentioned this in forum, it is okay, but still I will repeat it for the benefit of people who have not listened to me on this topic before. I have a number in my mind, 1 to 100. What is that number? How will you compute it? I'll give you a supercomputer. I'll give you access to this machine. Here, in CD Center. Unconditional, I'll give the key to you. How will you find it? What algorithm will you use? There's a number in my mind, it's a random number, and then you have absolutely no clue. But then I didn't even tell you. It can't be that just this. Because encryption algorithm, I have to pass on the values. So, here is something. I have a number in my mind, that is x. I add a random number r. This r could be positive, negative, 0, and the sum is 70. What is that number? You are now seeing 70. What is that number? The algorithm also you know. The number and the random number added is 70. This information also you have. What algorithm will you use to find x? The number is added with a random number. It could be positive, negative. You can't say that it should be less than 70 or something like that. My number could be 150 and the random number could be minus 80. Because of that you got 70. My number could be 0. The random number could be 70. Because of that I might have got the answer 70. Now what will you do? Again you see that you are completely clueless. This is called the random blinding technique. You use a random number to blind it so that the possibilities could be anybody, and then there is no algorithm that he can use. The only thing he can use is go too exhaustively, and if the search space for my x and r are very large, you will have absolutely no clue whatsoever, and then you are completely lost. Multiple? Yes, every time. I have x plus r1 is 70, x plus r2 is 100, x plus r3 equal to 49. What do you do now?
Estimate the random variable.
Huh?
Try to estimate the random variable.
How will you do that? What is the clue that you have to proceed? But my search space is very large. It has got some 10 power 50 elements. My number, the range of numbers. What estimate will you use? And estimating r is not really going to help because you have no idea of what r is. What r I have chosen, you don't know. I know x, I have r. I have done an encryption algorithm which has done this. You are seeing only this. Right? What estimation of r is going to help? Even if I tell you r is in the range between 1 and 1000, is it going to help? Yes, you can see you have no such bounds that are used. You have no idea what r I have used. That is the reason why this makes you sweat hard. Random blinding is a very powerful technique, extremely powerful technique. Unbelievably simple, amazing, but then what it has done is something remarkable. All properties are erased. X may have certain property, but X added with the R, everything is gone. Right? It has become a random number now. Random numbers do not have any specific property. Everything that X has lost. You may even check with my personal habits. I may be very superstitious about number 5, or my lucky number is 7 or something like that. So X may be a multiple of 7. Doesn't matter. X plus R has no property. In other words, even if you have some a priori information, in fact, historically, I will digress a minute. This is very important. You know how cryptograms were all solved? The cryptograms will be appearing in newspapers. Some English sentences will be given, and then you have to find out what is the meaningful English sentence that has been converted into the cryptogram. If you mindlessly try, it is going to take years. But what they do is that they do the frequency analysis. Because in English sentence, A's will appear with some level of frequency. E's will appear lot more. Z and Y very rare. Like this, you have a probability distribution or a property of the input is kind of known. How do they know that? They have taken large number of English sentences and then sampled how many A's, how many B's and everything, and then it's a statistical table. Typically, a random English sentence will have this kind of a distribution that they will apply. So what they will do is, they look into the cryptogram, which letter is occurring more frequently, that must be E, right? So they will make this kind of a guess, and within few trial and error, they will be able to do that. That is because the cryptogram is preserving the property. It is just that E has been made T, Z has been made A. So whatever property E had, T will have. Whatever property Z had, A will have in the cryptogram. The properties are visible. The distribution is visible. In that case, they know that okay, this must be mapped to E, this must be mapped to Z, and then with some trial and error, they will construct it and then win money, because you have to send within a day. Next day they will publish the solution, and whoever is sending the correct solution, a winner will be chosen and reward is. So you have to solve within a day. You can see that people desperately trying to solve that cryptogram, but they will use the pattern and often they are very successful in their guesses. That is because cryptogram, the C is preserving the property of message. If R, this is C, okay, X plus R equal to C. If C preserves the property of X, by analyzing C, I will try to narrow down on X. But what Shannon, okay, anybody who is born after Shannon must know about Shannon, must read his work, right? My personal appeal to all of you is that don't die without reading the paper on communication written by Shannon. Amazing paper. Landmark result. The intuition of what is security has been so well brought out, and then in those days the attacks were all done on this kind of probabilistic and pattern. Eliminate the pattern, it will disable the attacker. What is the technique? Random blinding. Beautiful thing that he has proposed. He built a lot of things on it. Fundamental results, foundations of cryptography was laid by Shannon, because he is also consolidating the information theory. Therefore, information security is naturally leaning on information theory. Okay, he is a pioneer. He did it at random blinding. Now, quickly, let me go to this idea. Idea is used on one of the encryption algorithm that we are going to use. Okay, but our topic is proxy re-encryption. So let's motivate that and then go back to the system. What is proxy re-encryption? It all started with a real world problem. Okay, this issue itself has started, it's a real world problem. Apple, it is selling a lot of iPhones, and Apple has music repository. You have to pay, and only for the paid subscriber the music is to be distributed, or the music file is to be distributed. Okay, this is the task. Apple buyers, millions all over the world are there. Centralized, for a while they handled, and later on they found it is unmanageable. Right? Okay, millions of users and thousands of their requests, and honoring them, and verifying the period of subscription, and then disabling them, enabling them, all of them is a huge task. So, but they don't want to give the file in plain. If they give the file in plain, you will pass on that to your friend, and your friend will pass on to somebody else, and afterwards nobody will buy that. Therefore, it has to be encrypted. Must be usable only by you and not by anybody else. Right? Therefore, they want to create an encrypted file and give to you. Let's say you have asked for a particular music file, you have paid for it. You know what Apple will do? Apple will ask, Apple has in its database all music files, okay? Millions of them, not one or two, all albums and all individual, everything encrypted. That is because if you attack that server and then if you obtain the file, you can sell it or you can give it to people, right? It will affect the business. It is there in an encrypted form in Apple database. It has to be encrypted and sent to you with respect to your key. So what Apple earlier used to do is, it will decrypt, take the original file and give it to the distributor in India. All mobile phones, iPhones sold in India, there is a centralized India or Asia, whatever it is. Let's assume India. Let's say in New Delhi, there is an Apple Center which keeps track of all the things, and then the Apple in US will decrypt the music file. It will send that music file to the center in India, and then it will say, because you have sent money to Apple, you have paid, I want this album, okay, music, whatever it is, you have paid. So Apple will decrypt that and send to the Indian center, and then the Indian center will make sure that it is reaching you. Okay. Sometimes, if in anticipation of certain large scale request, it may even ask, it will leave that file unencrypted in India. Quickly, when the request comes, you can, in other words, there is a delegation of handling the encryption task. In order to do that, there is a message M. So this is Apple, this is you. There is a proxy. Proxy is any third party. Okay. This proxy, it has got encryption of M under the key of A. Under the key of A has his own key, he has encrypted and then he has kept it. Now he will decrypt it and send M to P, and there is a key, for public key of this. Public key is used for encryption. Private key is used for decryption. So there is an encryption of U of M. But how this encryption of M is with him, public key of U can be obtained, and then he can encrypt and then send it. This is how encryption of a message in A is converted into encryption of the same message for you. Because for a different user, one user's file cannot be decrypted by other. Because only you have paid, it has to come only to you. So it will be encrypted only into your key, and even if you share that file to somebody else, it won't work. Because it is encrypted for your key. Alright? Therefore, what is happening is, there is no way in which the one that has been, a file that has come to you can be used by others. You may ask, can't I decrypt and then send it? For the time being, let us assume that that is difficult, and it has been made difficult in certain sense. Okay? So we do this conversion. Now, this is what has happened. There are some notorious Asian countries. They will have this M and they will start selling it straight to the third party. They make CDs out of them, fake CDs, and then fake CDs will flood the market. After seeing that the source of fake CDs that are flooding the market, that are hurting the business of the original album maker, they found out that one of the sources is the proxies, which are supposed to do only the job of reconversion. They have access to the original file, and then they are doing a lot of mischief. That's the problem. So Apple started a research on this. They want to still use that file, but then he should not get any information. He has to do the re-encryption, but without having the access to the original one. How do they do that? Right? This is the theme of today's discussion. How a proxy is going to work. Therefore, there is an algorithm to be executed by proxy. So he will have input, encrypted message under A's key, output, encrypted message under U's key. That algorithm will, this will take as an input, and it will give that as an output, but it will never have M in between. It's not that EAM is converted into M is converted into, no. There won't be any passage of M. From EAM to EUM, this proxy has to do, that is called the proxy re-encryption. And proxy will be given what is known as a re-key, A to U. There is a re-key that is going to be given to him. An algorithm will also be given to him. He has to use the re-key and the algorithm. It will generate, it will take input EUM, it will output EUM. It will not get any information about M at all. So he will do the service, but then he has no access to original M. Right? Beautiful mechanism. And now after this was done long back, and after that now you have cloud computing and other things. Cloud is giving service. Not only it is used as a data storage, right? The clouds are providing lot of services. So it has to deal with certain data. And then you may not want the original data to be simply be passed on or trusted, because you don't even know where the cloud is located, which rules and regulations are governing the cloud. Nothing is known, right? But you are using its services, and you are probably passing on sensitive data to that. You don't want that. Somebody has asked about certain, or even a government agency wanted some classified personal confidential data of your company. It's all stored in the cloud. Can you simply ask the cloud to pass it on that? And if it is maintained in the cloud as it is, it's a disaster. So you store almost everything in encrypted form. But if you simply pass on the encrypted form to the government agency or a third party, how will he use it? It is encrypted in your key. He cannot decrypt. Therefore, he has a public key. To that, it has to be re-encrypted. Nowadays, cloud services are also using this re-encryption technology to offer this kind of services of transferring confidential information from one source to another without even knowing what information. You authorize, here is the key, use this data on this key, and then whatever you produce, you give it to the party which he has mentioned. So Apple will say, Apple will give this key and this EA and ask the proxy and then send to M. That's all the information. So the moment you pay, the re-key will be sent. It will be using, and then all should happen within 1 second, 2 seconds, 3 seconds, like this. So it has to be very efficient and so on. Okay? Other things, algorithmic security, all other things also follow. It's not only statement of the problem at high level. When it comes to ground reality, you have to address a lot of issues. Okay? Let's now go to the system. How this is done. To visually see you and understand what exactly is happening. The system that I am going to present is very weak. This is the first system of its kind. It doesn't have all the desirable properties in its full form. It is doing the job reasonably well, but subsequent research has fine-tuned it and so on. But they require heavier mathematical machineries, heavy-duty math machineries. The math machinery that I am going to use, which is based on the first system is based on, is very simple. Okay? Therefore, its security powers or security guarantees are also weaker. We will also comment on the security, what it offers, what it doesn't, and all later. And then it opens up the whole area of research. Right? What are all the directions in which we can go further? That I will tell you after. You have to get one concrete idea of how things are done. Right? So next 10 minutes we are going to spend on knowing about a specific system. It's not a great system, but this is the first system. Usually that will be the case. First you solve the problem in some way, then you understand its capabilities and limitations, and then refine it, make it stronger and so on, and then the research opens up in various directions. Alright? So here is the algorithm. I'm going to give you an encryption algorithm. Alright? This encryption algorithm works as follows. Every user A is going to work on, all users actually in the community, they are going to work on the following two common things. What are the two common things? One is a prime number P and another one is a generator called G. So what is this P and G? G is a number between 1 and P minus 1. Strictly speaking, G is a number between 2 and P minus 2. G is a number between, and the whole cryptographic algorithms are working in the modulo world. That means the space of numbers that you are going to work with is 0, 1, 2 up to P minus 1. That is because everything is mod P. Mod P means divide by P, consider only the remainders, nothing else. So you are basically working in the remainder space, 0 to P minus 1, that's all. This is your world. These are the numbers you are going. Once P is fixed, this is all you are going to work. Alright? So on this you have the modular arithmetic, multiplication, division and so on. For example, if P is 11, 5 times 7 in the modulo world 11, okay, 35, and 35, because it is 35, it is 2. 5 times 7 is 2. 7 times 8 is 1, because this is 56, modulo 11. So if 7 times 8 is 1, 7 is called 8 inverse and 8 is called 7 inverse, because when you multiply two numbers and you get 1, 1 is the inverse of the other. Like your numbers, 3 by 4, what is the inverse? 4 by 3. Multiply these two, you get 1, right? Same logic. So you, in the modulo world, you have additive inverse, multiplicative inverse, and it's a very rich mathematical structure. Technically, it is called a finite field in the abstract algebraic terms. Okay, so this is what we are going. Then what is this G? G has a beautiful property that its powers enlist all the numbers from 1 to P minus 1. So G power 1, G power 2, G power P minus 1. If you consider this set, this is set theoretically 1 to P minus 1. It is set theoretically, not in that order. It won't, it will produce them in some random order, okay? But all values are produced. A number like that is called G. For example, 2 is a generator. This G is called generator because 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is, now 8 times 2, 16, therefore that will be 5, 2 power 5 is 10, 2 power 6 is 20, therefore it is 8, 9, 2 power 7 is 7, 2 power 8 is 3, 2 power 9 is 6, and 2 power 10 is 1. Now you can see 1 to 10 are listed here. Because for mod 11, 1 to 10. 1 to 10 is appearing as the powers of 2. Therefore 2 is called the generator. Why it is called generator? Its powers generate all the elements. This is not true for 5. If you consider 5 power 1, that is 5. 5 square. 5 square if you take, it will be 4, right? 25. And 5 power 3 is 9. 5 power 4 is 9 5s are 45. 1, right? That's all. Okay. Did I make some mistakes somewhere? Maybe I might have done, but it doesn't matter. You can see that this is not listing all the elements from 1 to 10. 5 is not a generator. 2 is a generator. So given a prime, who are all the generators? How to find a generator? All these things are ironed out in number theory. Beautiful number theory is done, mathematics. So the whole world can work on one such P, and what is that P? P won't be like 11. It will be a 1024-bit number, very huge number, 300-digit number. Very, very huge prime number. And you take a generator which is very large. Okay? This can be used by everybody in the community. How everybody will use it? This is the way they are going to use. Every user A will choose a random number A in this range. They will avoid 1, they will avoid P minus 1. 1 and P minus 1 are avoided. Other than that, any A he will choose. and then he will compute G power A mod P. This is called the secret key of A. This is called the public key of A. This is the way secret key and public key are. And public key by definition is public. It will be available in A's home page. You want to send a message to home, A, you have to encrypt. Encryption algorithm requires message and the public key. Message is with you, but where do you find the public key of A? Anywhere. He may make it open in his home page, or he may use a paid service who are maintaining public keys, public key infrastructure. So there are people who will maintain for you, right? So you can reach them out and obtain the public key of A. And you can encrypt and send to A. Alright? Encryption algorithm I have to specify. Similarly, you have B and he has his B, and this is secret key of B, and the public key of B is G power B mod P. This is public key. Now, the one question that you may ask is, of course they should be related. Then people know that this is the way they are related. Right? From public key is also known, I can obtain, can't I find your secret key? Because only secret key provides you the security and secrecy, privacy and all. Can't I compute? See, in this, what are all the things I know? I know G, I know G, I know P, I know this value because this is computed and then this is made public. I know this value, this. I want to know what this A is. Is it possible for me to find A? It turns out that up till this point, there is no efficient algorithm available to find that A. Technically, this is called the discrete log problem, because when the exponent is given and when the value is given and the base is given and the exponent is asked, it is log of that, and it is in the discrete world. Therefore, this is called the discrete log problem. There is no efficient algorithm available in the deterministic computing world as on today. Therefore, you can make public key. Public key and secret key is related. That relation is also known to the attacker. But will he be able to find in his lifetime the A? He will not. There is no efficient algorithm available. There are algorithms available that he can use any super duper computer, 1000 processor based system, multi-processor, anything he can use. He can't find A in less than 100 to 200 years. Therefore, your secret key is safe. Okay? So, that is the current status. That is the reason why we use, but the same P and G is used even by B, by C, by millions of users. No problem. Everybody should use one secret key and corresponding public key. Each user can have even millions of accounts. Even then, our world has got only 8 billion people. 8 billion times 1 million. Trivial number for the range of P, for the range of G. Therefore, absolutely no issues at all in practice about honor, no duplicates, nothing is going to happen. Every one of us can have million account and still we will not run out and run into others' public key or secret key. We can all have our, okay? All right. So, this is the case. What is the encryption algorithm? Here is the encryption algorithm. This is called, the security of this is called the mathematical hardness of certain computational problem. Same way, the encryption algorithm I can use, from the ciphertext you will not be able to get the original message because it is as hard as certain well-known mathematical problems. Right? Therefore, computational infeasibility is theoretically shown. That is called the security proof and security argument. Without security proof and security argument, if you simply propose a crypto system, the world is not going to accept it. Right? I have done this complicated computation, here is an encryption algorithm. Can you theoretically prove? This is the first question that is asked now. Now the subject matter has matured a lot because in the past people have designed a lot of crypto system, they are all broken and mathematically sophisticated, looking very complicated, everything is broken. So they want a mathematical guarantee that it is computationally hard. That one has to prove. Okay, the computational hardness of this, from this to this is known. Right now there is no polynomial time algorithm. Okay. Now, here is the encryption algorithm. Okay. If you want to encrypt according to the secret key, this is what you have to do. encryption of public key of A and M. This is public key of A, okay, power R, public key of A power R, G power R times M. What is this R? R is a random number chosen by the encryptor. The person who is encrypting will choose a random number R, okay, and this public key is G power A, therefore this is G power A R, G power R dot M. So you raise G to a random power, so you are going to get a random number, and that random number multiplies M, therefore random blinder. Like I have added here, this algorithm does the multiplication, that's all it does. So when you multiply message with a random blinder, that component becomes a random value. And this is G power A R, this is also random, R is random. This random number is chosen by the encryptor. Nobody in the world knows what random number is chosen. He is sending this C1, C2 across. He is sending this C1, C2 across. So C1, C2 will look like a total gibberish for anybody because C1 is a random number, C2 is a random. Two random numbers are going across. What do you make sense of them? Suppose 4 and 49 goes, what sense you will make? Suppose 9 and 81 goes, what sense you will make out of it? They are random. Whatever sense you can make out of one is what you can make with the other because they completely random. Right? This is what frustrates the. There is a formal way to prove all of that. We do not worry about it. Now, how do you unblind it? Because this G power R is to be knocked out. G power A R is there. From there, how do you get G power R? G power A R power 1 by A. A is known only to one person, and that person can invert it, and he can raise that G power AR to 1 by A, and he can get G power R. He can divide the second component by G power R and recover M. The person who doesn't know A is completely clueless on both first component and in the second component. It's totally random. Two random numbers are simply going across. The attacker or adversary, the person who is eavesdropping, won't get any idea. Beautiful method, right? Therefore, what you have to do is, you have to convert this into encryption under B, that is G power B R, G power R M. G power R M is the second component, so don't touch the second component. Somehow convert the first component to this. Therefore, the rekey is designed in this way. A has a secret key of his. A can get the public key of B, so A is compute rekey to be B by A. A is his secret key that A can compute. So A can compute the rekey, and A will compute the rekey and give it to P. Now what P has to do is, his responsibility is, first component raised by rekey. First component raised by rekey. First component is G power AR, raise this by rekey, which is B by A, which is going to give G power BR. Second component don't touch. This is the instruction for the proxy. I am sending you a rekey, raise the first component by the rekey, don't touch the second component, send this to B, that's all you have to do. Now he is raising it, and it will be another random pair. He won't make any sense out of it. He is not going to get any clue about M. So without knowing M, he has done the job of transferring the ciphertext of one to ciphertext of another. Ciphertext for A is converted to ciphertext of B with the help of a rekey, which is not even generated by him. It is generated by A. It has A's secret key. Therefore, he has nothing to do other than just do the job of raise the first component and pass it on, and it will work. Okay. Such a beautiful method. It's a first cut solution. As you can see, it doesn't give any handle to proxy and other things, but it has got obviously certain weaknesses. There are, in view of constraint of the time, it's already 11:30, so we are going to stop at this point. And questions on what if the adversary is collaborating with B. So, for example, if this adversary talks to B and collaborates, because B's public key is known, A's secret key can be knocked out. Therefore, everybody will know A's secret key, which is disastrous. This scheme is suitable only for honest but curious or passive adversary. If the information he has, he will try. When he can't do, he won't do anything else. Active adversary, on the other hand, can do a lot more damage, and for that you need a stronger system and so on. For passive adversary, this is okay, alright? But, so how do you extend it for, how do you scale it up for multiple one? Like this you have, I'm sorry, this, I have to cut this and 1 second. So, like this you have a variety of extensions, and can it be changed? Suppose it is from B to C, and for various other database and then data center application and cloud applications, your requirements are even more different and more functionality is to be added. So proxy re-encryption, which started not long ago, hardly 25 years back, it started with this simple system, this is a Blaze system, right? To something, these people, again the same person. So in various directions and other things have, and now it is a very rich area of research thanks to the application of variety of contexts. Okay, so I stop at this point. You can talk forever because art is long, as people will say, life is short. There are so much done by so many researchers and intellectual gems, and then beautiful ideas have been developed based on this statement of the problem. And again, relevance in the quantum computing and then post-quantum models and lattice-based cryptography and various models in which this has to be extended and looked into. This problem has to be solved with various functionalities, additional requirements and different models and different security environment. Okay, so oh my God, this is all right. I stop at this point, and any questions you have? Yeah, please.
So when we are passing it, well, theoretically it makes sense. When we are passing on the E key, isn't E by A going to be a floating point, and that might cause issues down there?
No floating point here, all are integers.
Yeah, but like both of them are integers, so they are not like E is not guaranteed to be divided by A, so that will.
Oh, okay. I must tell you that B by A actually means the following. B by A here means B times A inverse mod P. This A inverse is computed in the modulo world like this, right? Because this into this is 1. So, in fact, you can find out the inverse with respect to P, the integer inverse with respect to P, by a well-known algorithm called extended Euclid's algorithm. Okay? So, to extended Euclid's algorithm, you give as an input both A and P, A inverse can be computed. That will also be an integer. And B by A is nothing but B times A inverse mod P. Therefore, this can be computed and this can be all computed very efficiently. Therefore, that's what it is. Hence, it's not floating point. It's still all our computation is in integers, only integers. That's the reason why only number theory is going to be used. No continuous math. Everything in cryptography is going to use extensively the discrete math models. Something really urgent and desperate. The same person again. I'll attend later. Anyway, so. One second. I have to cut this, otherwise it will ring and disturb. Okay, it has gone to voice. Tell me.
So in this model, we are basically assuming that the person who is sending like the rekey thing, they know the secret keys of both of the.
The secret key of B is not needed. Only public key of B is needed. Okay. Oh, yeah. In this case, yes. Yeah. I'm sorry. Yeah. In this case, the secret key of V is also known to A. Yeah. In fact, there is another algorithm in which the public key of B is used, secret key of A is used, because A is generating the rekey. he is going to use these two information and generate the rekey. But that algorithm is more complicated. That's why I didn't use that. Good that you brought this for discussion. One major weakness of this is A must know the secret key of B. Alright. For a small community this is okay, but for large community this is not. The reason is the way in which the secret key will be made known to A is to be done independently. You cannot use the same communication channel. Right? Therefore, there is a protocol that will allow them to exchange the secret keys and then bring that to a point and all. And that cannot be executed by Apple with every user and other things. Therefore, that's another practical limitation of this. This algorithm converts, but then it requires the knowledge of secret key of B. Right? The algorithm that is using the secret key of A and public key of B is more complex. Really complex. 2 orders more complex than this. In a short time, it's difficult to say. Also, it requires what is known as bilinear pairing and other abstract algebraic constructs. That's the reason why I didn't touch upon this. This is very easy to understand what is actually going on here, so I chose this. But this is highly limited. I mean, this is not used in practice. It is only used to teach and introduce the topic. Practical algorithms are more complex and different. Okay, and thanks for bringing out the point that B by A is to be viewed in the discrete world. That's also another important point you should note down. Yeah. Any other question? Absolutely desperate. Okay. All right. So if there are no further questions, I stop at this point and thanks for. There's somebody more interested in listening to me. So.
Thank you, Professor, for enlightening us this morning. From the database community, we have a small token of thanks being presented to Professor Pandurangan by Palak from the database community.
Thank you very much. Take a picture. Yes. Proud picture. Thank you very much.
Thank you, Professor, for being such a great help in planning this event.
Excellent. So let's all go for a coffee now, and then maybe after a coffee break we can assemble.
Yeah, sure.
15 minutes. We will cut down the coffee break to 15 minutes, and then.
Tea and coffee served outside.
Yeah, outside.
Yeah.
By 11:45 we'll have the next talk.
We have the next talk at 11:45. So.
Anira. अभी तो आ रहा था जो ब्लैक आ रहा सिडनी वाला वॉक थ्रू कैमरा स्टोरी या वो सब शिट है तो ब्रो उधर ऑन ही है ए विंडो कैप्चर्ड हां नो 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 डिस्प्ले कैप्चर भाई ये कैसे सेटअप करते हैं डिस्प्ले डिस्प्ले विंडोज या सेलेक्ट get 13.
Check, mic check.
Show me. Find the answer. First I one yeah, that's what I'm doing. It's here present. Fine.
Hello everyone, thank you for joining. I will be talking about intent beyond instructions. So what we will be covering in today's topic is, firstly we'll try to understand our ability to figure out intent. Intent is essentially what a person wants, not necessarily what they say. Because we have ambiguities in natural language. So we'll figure out our ability to detect ambiguities and resolve them in natural language statements with respect to code writing tasks. Then we will move on and look at a prototype system which does the same. And we look and quantitatively analyze how good that system is. And finally, we'll move on to if LLM, why LLMs fail to follow even simple instructions, and even understand if they even know when they follow instructions. So moving on to the first part, intent and the ability to find ambiguity. So we'll go over some definitions. A function signature is the function name and the type hence. The doctrine essentially explains what the function does. And doc test is an example input-output which the function must follow. To explore this idea of ambiguity in code writing tasks, a paper discusses these problems, calling it probable problems. The reason is these problems are deliberately made ambiguous, and there's a mechanism to probe these ambiguities to understand what the hidden intent is behind these problems. So we ask the question, how well can we probe such problems? Well, you might say, why should I care to even look at such problems? No one is going to give me a deliberately ambiguous problem, right? However, multiple research has seen that real-world specifications for code writing tasks are often ambiguous because they are written in natural language. The reasonable but unstated desire of the client. And failure to clarify these ambiguities can lead to can be very costly in software development. So we move on to probable problems. These problems were a competitive programming style event was organized by the authors to understand the students' ability to probe these problems. There were all college students part of ACM organization. There were 67 students in 2016, and they were given 5 probable problems to solve in 2 hours. These problems are checked by prompting the state-of-the-art AI models like GPT, Claude, etc. And these models were unable to generate the accurate code results, accurate code on these questions. So the question is, how can students probe these problems? Well, there's an oracle or ask the client where you can give a particular input and ask what that function produces on that output. So essentially, you give the input, and the oracle will tell you just what is the desired output on that input, and the idea is that the students will then infer from this input outputs. They can do as many probes as they want to, and infer what the objective of the function is, and then proceed to write code on it. So an example of the one of the probable problems which were used in the contest is this. So the problem given to them was, write a function first positive integer that takes one argument, a string. Your function should return the first positive integer in the string. So there are 3 ambiguities present in this problem statement. First, the return type and in the blue box was not mentioned. in the problem. Secondly, what do we mean by first positive integer? That was not defined in the problem statement. This is how the authors define it. And third was behavior on if no such word exists was not clarified. So the idea is that the students generate these inputs, which and by looking at the outputs which the oracle wants on these inputs, they will infer that this is what the authors mean. This is the intent. So the results are the following. So there were four types of ambiguities. Definition, for example, in the previous case, we did not define what we mean by first positive integer. Behavior on certain inputs. Example, no word present in the previous problem. Return type not clarified, and tie breaking mechanisms. So the table you see on the right, each cell represents the percentage of submissions which were able to accurately uh, probe these ambiguities and find the intent behind them. For example, in P1, for the behavioral type ambiguity, only 30% of the submissions were able to accurately find what the intent was. On average, only 20% of the ambiguities were found out from were able to be probed by the submissions. And I have highlighted some specific ambiguities. For example, if you look at problem 1, 2, and 3, we have 30, 45, and 50% students didn't realize that there could be many such outputs instead of a single output. What we really see is that rather the inability to probe these questions, especially when you have been told that these are ambiguous questions. In real world scenarios, it's not necessary, you are not explicitly told that the problem can be ambiguous, right? You have to infer that maybe it's ambiguous and probe it yourself to find clarifications. So another study was done in a much larger scale with these probable problems in a introductory course at the University of Auckland. There were 1,028 students enrolled, and they introduced 3 probable problems, P7, P8, and P9. And they are the same format of ask the client, and where they can ask the client on this input, what is the desired output. These were the 3 questions. For example, if we take P7, implement a function to count the number of integers between a and b in an array of length n. There are 4 ambiguities which is present in this problem statement. Firstly, it is not mentioned if a is to be included or b is to be included while counting. It is not clarified if a is always less than b. It is also not clarified what if we cannot find any integer between the 2 numbers a and b, what should be what we should return. So these are the results. Let me just go back once. They also provided a default probe, a default example of a doc test which can be submitted. If you notice, these default probes do not provide any more information than what is already given in the statement. That is, they don't provide any information to explain the intent on the ambiguities which is present in these problems. So there were total 44,000 probes submitted, out of which 3,600 were default. Excluding the default probes, this is the analysis. So the x-axis shows the number of probes submitted by the student, and the y-axis is a cumulative distribution of the students. The students are divided into 4 groups in retrospect on basis of how well they performed in the study, and it was found that on average the group A, which did the best, submitted way more probes than group D. So it is a clear indication that probing does help figure out the ambiguities and the intent of the user or the person who gave the problem statement. So there's another question which we mentioned, that models were unable to generate, AI models were unable to generate the correct code on these probable problems. So the question is why? Well, that brings us to why don't they ask questions? Because the only way to clarify the ambiguities is to ask questions to the user. And the reason they don't ask questions is because they are encouraged to arbitrarily fill in some assumption on the ambiguities. So, for example, there is reinforcement learning through human feedback, where a much higher score is assigned to answers which fill in ambiguities with their own interpretations as compared to asking clarifying questions. Another thing is they don't possess true meta-knowledge, which is they don't know what they know. So because of these reasons, LLMs don't ask clarifying questions. I'll give you an example. So this is Copilot. This screenshot was taken a month back. We are providing the function signature, docstring, and doctest, an ambiguous specification, and Copilot is, just immediately suggests you a solution. Now, if you notice, there are multiple assumptions in this solution. For example, we never clarified what we want to return if no digit is present. It automatically assumes that the desired return is -1, and so on. So we need to find a way to be able to, ask these questions. Someone to ask these questions to clarify the intent. In conclusion, probable problems represent real-world scenarios where you have ambiguous thought specifications. We have also and hence there's a need to clarify these ambiguities. Both humans and AI is subpar in probing these ambiguities. So the question is, can we develop a system to automatically probe these ambiguities and then resolve them as per the user's intent? So this is the prototype system we present, ambiguity resolution with human feedback. So what we are doing is, now your ambiguous statement can have multiple interpretations, right? Someone can interpret that you want to return -1, someone can interpret you want to return something else. So we define reasonable interpretations as all interpretations which follow the conditions given in the docstring. The ambiguities have their own interpretation, and hence you have multiple reasonable interpretations. For example, in the min index problem, we did not clarify what we want to return when there is no such digit present. So one possible interpretation is to return -1, and another possible interpretation is to return the length of the string. These are both valid interpretations, but obviously the intent of the user either lies in one of these two interpretations or something completely different. So the model consists of three main components: initial code generation, test input generation, and code correction. Moving to the first component, initial code generation takes the user input, which is our ambiguous specification S, consisting of the function signature, docstring, and doctest. The second part is, we then go to the LLM and ask it to generate a candidate implementation, a code, on basis of this user specification. So the LLM will generate the code, filling in the ambiguities with its own interpretation. And after that, we just ensure it passes the doctors which are specified in the user specification. After this, we generate a list of inputs using two methods, one an LLM and using crosshair. So these inputs are generated to help us probe the code generated by the code LLM. So what is crosshair? Crosshair is a symbolic execution tool which essentially helps you explore all paths which your function leads to. Think of it this way: you have a function which has a if condition, if x is greater than 3. What crosshair does is, it creates a dummy variable x and it passes it through this function. When it reaches this if condition, it will split into two parts, with an x which is less than 3 and an x which is greater than 3, to explore both scenarios. This way it can explore all the possible paths which your function leads to and help generate some interesting inputs. What we do with these inputs is that we run these inputs on your candidate implementation C generated by the code LLM, and we get a list of outputs. We call these input outputs as the doctors. These doctors are there to confirm with the user what their intent is. So if you see on the right, we have an image here of a tool. So for example, one of the inputs suggested by the crosshair or the code LLM was an empty string. So now on an empty string, either the user, if the user's interpretation was to return -1 on an empty string, which is what our code LLM's interpretation also was, the user can simply accept that solution, or say the user wanted to return the length of the string. In such a case, they can reject it and mention their desired output. What this does is, it helps us deduce from these doctors what is the user's desired interpretation. We can see the pattern which is present in these doctors and then understand what the user really wants on these interpretations. So what we do is, we take these corrected doctors, we go back to the LLM, ask it to correct its candidate implementation on basis of these doctors. We then ensure if the candidate implementation does really pass all the doctors. If it doesn't, we can go back to the LLM and have this loop run multiple times till the time we reach our desired code. In the analysis of our tool, we do not have this loop because we want to essentially present a lower bound on the efficacy of our tool. To summarize, we take the user specification S, function signature, docstring and doctest. We then pass it to the LLM to generate a candidate implementation C. We generate inputs using LLM and crosshair, and we run these inputs on the code to generate a list of outputs. We show it to the user and get human feedback, and then accordingly either we modify the code or just show the code to the user. We used Quen 32 billion parameter for our experiment for our analysis and the default parameters. So now we ask two questions. Firstly, how effective is our input generation, which is how good are the inputs we are generating for it to be able to probe these probable problems, these ambiguous statements. And secondly, how effectively our system is able to use this human feedback to generate the correct code. So we tested our tool on 6 problems. 3 of these problems are taken from the probable problems paper by Denny et al. The 3 problems I showed you earlier, P7, P8 and P9. For each of these 3 problems, we chose the desired interpretation which was mentioned in the paper. What I mean by desired interpretation? The paper proposed that each of these problems can have 16 possible interpretations each. And one of the interpretations is the desired interpretation of the authors. So we take that as the target interpretation and accordingly fill the doc tests, those accept and reject questions. We ran the tool 100 times for each problem. We created 3 other problems to test if our tool is agnostic to the interpretation we take. What I mean by that is, we took for each problem, we took each interpretation as a target interpretation and ran it 25 times to see if our tool was able to give the correct response irrespective of the interpretation you take. We have 2 mechanisms to evaluate, IAR and CAR. IAR is input ambiguity resolution. It is the fraction of incorrect implementations which were discarded by our test inputs. Essentially, for example, we had a input as an empty string, right? That empty string was able to discard the interpretation that on if no digit is present, you want to return -1. Say the user wanted to return length of string. So you are discarding that interpretation because you have a doc test with input as empty string. Similarly, we do code ambiguity resolution, which tests the does the analysis for the final code generated. It is the fraction of implementations which is inequivalent to the incorrect interpretations. So here again, let's say you have a code generated, you run an input which can probe the ambiguities and see what the output is of that code. And then you can analyze on these ambiguities, the code was able to correctly generate what the intent was able to capture the intent, and on these ambiguities it was not able to. So for our IAR, for P1, P2 and P3 we reach a score of 1. What that means is, in every single interpretation for each problem, our system was able to generate inputs which probed all of these ambiguities. And hence, because we can probe these ambiguities, we know exactly what is the intent. P7, P8 and P9, the IAR is not 1, however it's pretty high despite having a much larger number of interpretations, 16 each. In P9, I want to focus on P9. So the problem was implement a function to find the first vowel in a string. In one of the ambiguities, our input was not, our AR chip was only able to generate an input capable of probing it only 12 times out of 100. So the ambiguity was, you can interpret first vowel in a string either by order of the vowel or order of the index. What I mean by that is, here if you look at this example, order of the vowel would dictate if you have a A present, return A. If you have A not present, E present, return E, and so on. So you would return E by the vowel order, but return O by the index order. However, our system was only able to generate such inputs in 12 cases, and hence In rest of the cases, it was unable to generate inputs which can probe this ambiguity. Let's look at the code ambiguity resolution. So what the pass at one metric basically says is the number of successes by total attempts. And we notice again for P1, for all interpretations, it generated the code correctly in all the runs. Similarly for P2, it's a pretty high value for both pass at one and CAR. In P3, however, for the I2 interpretation, it was never able to generate code. Same for P9. I want to highlight that our IAR was 1 for P3. However, it was unable to generate the correct code in any run. I will come back to this later and ask why this is the case. So the poor performance for P9 is unsurprising because we were unable to generate inputs which probe that particular ambiguity. So of course, it's impossible to expect the LLM to be able to find out the intent. However, we still had a high CAR value. What that means is that even if we were unable to generate the correct code, most of the ambiguities were still detected and correctly resolved. So you can say that if our system is incorrect, it is likely it is to be subtly buggy and not completely incorrect. In conclusion, we present a prototype system that uses off-the-shelf components to effectively resolve ambiguities. Of course, future work can look into more diverse code writing tasks, more complex code writing tasks. We just focus on simple Python functions. It will also be useful to evaluate if this system is actually useful in practice by students and programmers when probing such problems. Now, I want to rewind back to the question why, despite being able to generate inputs, which for example, in P3 and P9, P8 and P9, which had inputs which could probe these problems, our system generated inputs capable of probing these ambiguities, the LLM still failed to correct its interpretation on these ambiguities. Which brings us to the question, why do LLMs fail to follow simple instructions? It's a simple instruction that we have these doctors represent the intent, follow it, yet it fails to do it and comes up with its own interpretation. So we must ask why LLMs don't follow instructions. In this talk, we are only going to be covering a subset of this problem, which is, do LLMs even know when they are following instructions? So there's a benchmark called if-eval, which is used to judge the capability of these LLM to be correctly answer questions and follow instructions. So the authors, so the paper by Hio et al. Developed an even simpler dataset which only consists of simple instructions, such as do not use the word apple, answer only in lowercase. To just explore if we have a single instruction, is the LLM able to accurately, does the LLM know for simple instructions if it's going to follow that instruction? Before we go ahead, we need to understand how LLMs understand language. So what happens is that your text is divided into words. These words are called tokens, which are then represented by a vector. It's essentially an abstraction to understand the meaning of these words for an LLM, since obviously machines understand numbers and not language. What that means is that each of these, think of a vector and it has some components, right? Those components represent the characteristic of that word. And look at this table, for example. We have, say we have a 4-dimensional vector. And there are 4 components, say royalty, masculinity, femininity, age. So the values in these associated with these in the vectors for the words essentially represent the characteristics of these words. So to probe the instruction following ability, what the authors did was create a simple machine learning model which just said yes or no. So on basis of the embeddings is the vectors generated from the tokens. On basis of these embeddings, they train the model on these embeddings to understand whether they can predict just on basis of the embeddings if the LLM will follow the instruction or not. So there's a metric to calculate this. It's called, so we have a graph of true positive rate versus false positive rate. You don't need to understand it. Just understand if you have a high AUROC, it means that the model which they created, the probe, was accurately able to predict whether the LLM will follow the instruction or not. So these are the results. I won't go into detail. There are 3 points which are to be 3 key points which we can look at. Firstly, it is so the probe is trained on particular data set, and when the probe when their model when they tested the model, they found out that they are accurately able to predict if the LLM will follow instructions when the task is generalized but not the instruction type. When you do the instruction type generalization, then their model fails. But the reason this is important is we have high values for first token and last token. What first token represents is before even the LLM starts generating the response, after it has just analyzed the question, you have a high chance of predicting if the LLM will follow your instruction or not. And the values of first token are pretty much equal to the last token, which is after generating the response, they did follow the instruction. What that means is, even before the LLM starts generating a response, you can predict whether it will follow your instructions or not. And it's really powerful because then we can intervene. We realize, okay, it will not follow the instruction. We can intervene and have corrective measures implemented to make it follow our instructions. So, recap, we have ambiguous problem statements in real life and as well as in software development and code writing tasks. And we present a prototype system, ARHF, which is a promising prototype to explore these ambiguities and able to resolve these ambiguities. And we also ask if LLMs know when they follow instructions. They sometimes do know when they're following instructions. And more importantly, we have a way of knowing, even before they start generating a response, whether they will follow instructions or not. And hence we can intervene and make some changes to ensure that they follow the instructions. These are the references. Thank you very much. Any questions?
I just want to make a couple of observations. One is typically if you look into the serious coding part, industries and other things, they have coding methodology. They want to have an internal format and way in which the codes are to be developed and all.
Right.
If you look at an ad hoc coding, everyone will write program as it occurs to their head.
Right.
And that will have a lot of issues. The point is whether professionally built code have these kind of issues is one thing that is to be looked at, because they are addressing all these problems long back, even before the LLM and other models.
Right.
The software engineering principles, if you look at it, the way in which a code is to be developed, and so there will be internal mechanism. If you take, for example, the training period for coders in Microsoft, how to write a binary search program, they train for 4 weeks. You will be wondering what is there to train on for writing a binary search code. We write in 3 minutes and then submit for an assignment and get some marks. But in Microsoft, to tell you the local customs, the training that is given on that is as long as 4 weeks for binary search. Right? So you can see the generalization, the types and various issues they are bringing in and all. So whether such a professionally built code which are following certain standard practices, best practices or whatever you call it, but there is an internal practice that is guiding the development. Whether they have these kind of problems, we have to see, number one. Two, most of the times the code part ignores the testing, also ignores the comments. Comments are given only to disambiguate, and comments are given only to provide more clarity. But none of the executions will take care of that. All your studies based on the execution might have, but is there a way in which some comment part of the code also be taken into and then certain resolving can be done is worth looking at? Because the example that you have shown, they are all written without any comment, but if you look into the professionally developed code, a 4-line code will have as many as 20-line comments.
Yeah.
Right? That means there is a lot more communicated by the coder,
Right.
and that information is available in the code. Whether these LLM models can take any advantage of those kind of things would be worth looking at, because none of the regular code analysis would take that. Because we have the ability to look into various other aspects in the LLM framework, such things can, any additional help, like you have said, the human interface.
Yes.
Before even coming to the human interface, is there a formal mechanism in which the comments can be used to remove certain ambiguities? What looking at?
What I want to clarify is what you pointed out, that professionally written code has a lot of comments such that there is no ambiguity present. But that is after the programmer knows exactly what is to be written. Here the problem is, let's say from the user's end, they want some particular, users aren't necessarily programmers. The person giving the task to a programmer is not trained to ensure that no ambiguity is present. So that's when the question comes that the statement that the programmer is getting might be ambiguous. So how do we resolve that ambiguity? After the programmer is clear of the intent, they will write great code with all the
No, there is a test team that is looking at various things, right? That gives a feedback for the developer, and then, so if you look into the program development environment in an industry, the way in which the thing, in fact, in spite of all of them, Microsoft is sending weekly bug fixes, Apple is sending monthly bug fixes. It's not that it is error free or we have no problem whatsoever at all and all. It is still there. But the point is, half of them are found out after it is deployed in the real world, and some user pointing out saying that, well, it doesn't work for me, and the whole thing is that I'm not referring to the bug. Weakness in the specification is what I'm pointing out. So whether any of these kind of things could be used, as you have said, in the development process there will be ambiguity. Probably in the development part phase, this may be somewhat helpful.
This was designed initially for novice programmers,
right?
For them to understand that these are, and then clarify these ambiguities.
No, but while the sophistication may vary, the depth of the problem also grows, and then it is felt at every stage of programming.
Yes.
Programming is a task that is never done perfectly ever under anything. It's almost like a very ideal goal.
This is just a prototype system, and it can be built upon even for even to be used by the industry.
But still, we should need mechanisms to find issues in any coding developed in any way. But the point is that if it can take the help of comments or few other things also, it can probably help a little more. You can bring in human maybe after some more stages.
Right.
Just more a suggestion than what if the code is written with very minimal comments or no comments. Then that step doesn't make sense. The point is, usually since that is available, then something needs to be done. Whatever is the help that AI tools can use in a profitable way, that can be incorporated to increase the reliability of the computation. Okay. Just a comment, it's not a question.
Any other questions?
Any other question? Since the recording is there and it is going online, I request the audience to not to converse with your neighbors. Okay? That will all interrupt. Even I am getting disturbed when the speaker is given. Then if it goes like this, it will be difficult. So I request perfect silence and interacting, of course, with the speaker is a must. That you can always do, but kindly do not indulge in conversation with your neighbors. Yeah, go ahead.
Thank you.
Next.
After all the talk of LLMs, let's pause for a moment and examine the quiet patterns that surround us every day. Next up, we have Archana and Ramnath, and they will take us through Voronoi Sweeping Beauty, a journey into the world of Voronoi diagrams. So I welcome Archana and Ramnath to come and present.
Is it audible? So, hello everyone. Today we'll be talking about this geometric pattern that you see here. And firstly, this is a very cool image to me. And this is a beautiful geometric pattern that you find a lot in nature, everywhere. Crystals model like this. In nature, a few cells grow like this. You see this, and in a lot of occasions, nature divides space like this. We'll be unraveling why these diagrams are so geometrically good, mathematically good, and comes often why nature shows up this pattern everywhere. And these are called the Voronoi diagrams, and we'll see how to construct them, how to define them, and some cool properties about them. We see the skin of giraffes, right? So those cells, the skin cells and the diagram here as well slightly matches with Voronoi diagrams. And this is an image of soap froth. Bubbles divide the space, and the pattern in the froth is similar to a Voronoi pattern that I showed you in the initial slide. Not just nature, this turns up a lot in art as well. You can create really stunning images with fractals from Voronoi diagram. Basically, you create a Voronoi pattern and then you keep creating Voronoi patterns inside and you will get some fractals. And this fractal you see right here is the representation of a leaf on a microscopic level. So yeah, these patterns are found in lot of occasions of nature, and these are very space optimal. How and how exactly and why is what we'll be thinking. So let's start off with the definition. What exactly are Voronoi diagrams? So let's think of this problem. I'm in a city and I have n sites, n post offices. So my question is, how will I divide the city into regions? Say I have n post offices or n site points. How will I divide the city into regions such that each region will be catered by that post office? What is the obvious thinking that if anyone is in a location, they will go to the closest post office. So I have to divide my whole plane into cells, or I have to divide my city into sub-regions for each post office with the property that I take a point in a cell and I compare the distance from every site, and for all the points in that cell, the closest site will be this point itself. So, Voronoi diagrams are mathematically defined as a subdivision of the plane into n regions if I have n site points, such that the Voronoi region of a point, a cell, is the collection of all locations such that its closest site is the point itself. So, the Voronoi diagram is the collection of all such cells. I call these as site points, I call these as Voronoi vertices, and I call this one as Voronoi edges. Now that we have defined Voronoi diagrams and how and the importance of it, and it has a lot of applications, our goal as a computer science should be how to construct this efficiently, how to build the Warnai diagrams, what are the algorithms, and we'll be looking into that.
So let's start with one side. So when there is just one point on the entire plane, all the points in the plane are closer to this point. So the Warnai region is basically the entire plane. Now, when you have 2 points, what we'll do, we'll construct the perpendicular bisector between these two sides. Why? Because we know that all the points on the edge, on this perpendicular bisector, are equidistant from both the sides. And if we look at this half plane, it is basically set of all the points which are closer to this side, and similarly, all the points on this other half are closer to this side. So the Warnai diagram for 2 points is basically this, 2 regions, these 2 half planes. Now look for n collinear points. So the Warnai diagram for n collinear points is basically series of n minus 1 parallel points which divide the space into n regions. Okay, so now let's see the case with 4 sides. Let's just focus on this side in the center. Let's call it P. So how we can get the set of all the points which are closer to P than any other side? So what we'll do, we'll first construct the perpendicular bisector between these 2 points, and it is clear that all the points which will be below this half, this perpendicular bisector will be closer to this side. So then we will construct perpendicular bisector between these 2 points, and all the points above this perpendicular bisector are closer to P. And finally we'll make the last perpendicular bisector between these 2 points, and all the points on the right of this perpendicular bisector are closer to P. So the region that you get by intersecting all the 3 perpendicular bisectors consists of all the points which are closer to this than compared to any other points, and that's how you get the Warnai cell or the Warnai region for this side. Similarly, you can do for rest of the sides. Let's see what is a Warnai edge. So edge is basically a segment of the perpendicular bisector. So it is set of points which are equidistant from these 2 sides. So this edge is basically all the points on this edge are equidistant from these 2 sides. And what is a Warnai vertex? A Warnai vertex is formed. It's a point where 3 or more Warnai cells meet. So it is formed basically by the intersection of 3 or more perpendicular bisectors. If you look at this vertex, it is formed by the intersection of this perpendicular bisector, this, and this one, which is the perpendicular bisector of these 2 sides. So as you can see, the Warnai cell for this side in the center, it's bounded with a closed polygon. We call this cell a bounded cell. Whereas for the rest of the 3, their regions, they extend to infinity in the plane, so they are unbounded. So what we saw here is that we can construct a Warnai cell by finding the intersection of the half planes which are closer to this side, right? So we have an idea that if we can construct Warnai cell for one side, we will do it for all the n sides, and we can construct our entire Warnai diagram. So let's see how this half plane intersection method works. So when you have 2 points, the Warnai region for this side is basically this entire half plane. When you add one more point, now you will have 2 half planes, and you take the intersection of them, and it determines the Warnai cell for this side. Then if you add one more point, again the Warnai region is the intersection of these 3 half planes, and that's how you can do with n points. So if you have n points and want to construct Warnai cell for one of the sides, you can construct n minus 1 perpendicular bisectors and take the intersection of all the half planes which are closer to it. That is the half planes which contain it. Okay, so let's see what's the cost of constructing Warnai by this method. So in this method, for every side, you are first constructing n minus 1 perpendicular bisector. So that is order of n. Then you take the intersection of all those n minus 1 half planes, and there is a standard classical algorithm which is order of n log n. and you do this thing for all the n sites. So total cost is basically n times n plus n log n, that is n square plus n square log n, which is basically order of n square log n. But the point is this method efficient? Do we really need to have computations of n square log n to compute Voronoi diagrams? Let's see. So to create Voronoi diagram, we draw perpendicular bisector between every possible pair. So how many possible pairs are there? NC2, which is order of n square. And we know that intersection of order of n square line can give you order of n square vertices and order of n square edges. But do we really need order of n square vertices and edges in our Voronoi diagram? So if I told you that the Voronoi diagram contains just order of n edges and vertices, then this method is highly inefficient and computationally very expensive to use order n square log n computation to create a much simpler diagram, which is order of n. So indeed, Voronoi diagrams have edges and vertices which are order of n, and we will see an elegant proof for it. So our claim is for, okay, so n is number of sites, v is the number of vertices in Voronoi diagram, and e is the number of edges in Voronoi diagram. So our claim is that for n greater than 3, greater than equal to 3, the number of vertices in Voronoi diagram is less than equal to 2n minus 5, and number of edges is less than equal to 3n minus 6. So let's first prove for the trivial case when you have n collinear points. So for n collinear points, we saw that there are n minus 1 edges, and since all these lines are parallel, they will never intersect. The number of vertices is 0, and this satisfies our claim. And now look for a general case. So basically there is Euler's formula which you can apply for connected and planar graphs, which say that sum of number of vertices times number of edges plus number of faces is 2. But can we use Euler's formula for Voronoi diagrams? Are Voronoi diagrams graphs? So what is a graph? So a graph is basically collection of vertices and edges such that every edge is connected to 2 points. So is a Voronoi diagram a graph? The answer is no, because we saw that there are unbounded edges. So these unbounded edges are just half length which are connected to one vertices. So therefore we can't use Euler's formula for Voronoi diagram. But is there any way we can tinker with our Voronoi diagram and make it a graph? So yes, what we will do is we will introduce an abstract point at infinity denoted by p infinity, and it will act as a cap, and we will connect all the unbounded edges to this p infinity. So now our diagram is planar, connected, and it's a graph. So now we will use Euler's formula for this Voronoi diagram. Now the number of vertices is v plus 1 because we introduced one extra point. E is the number of edges. The number of faces. So we already saw that a Voronoi diagram with n side divides the plane into n regions. So the number of faces is n. So here we have one equation with two variables, and so we need one more equation. And let's see. Okay. So what is degree of vertex? So degree of vertex is basically the number of edges which are connected to a vertex. So when we sum the degree of all the vertices, basically we are counting the number of edges, the total number of edges in the graph. But we are counting every edge twice. How? Because every edge is connected to two vertices, right? So when you v1 and v2. So when you add degree of v1 and then add degree of v2, this edge was counted twice. So similarly, all the edges were counted twice. So therefore, we have this equation. And moreover, we also know that the degree of any Voronoi vertex is at least 3, because a Voronoi vertex will only be formed when 3 Voronoi cells will come together and they meet at the vertex. So degree of the Voronoi vertex is at least 3.
No, that also comes from the fact that the points are in general position.
Right.
That
If it's degenerate, then
degenerate cases will reduce
correct.
to the smaller bound, which you have mentioned in the first one. Yes. So we should discuss about or discuss that points in the general position.
Right.
This bound will go. Otherwise, degree of V can be even 1.
Correct. Correct.
Even if you introduce point at infinity, won't have that property. But if the points are in general position, then no three are collinear, and they must form a triangle. And this condition, okay.
So the minimum value of this term on the left side can be 3 into the 3 times number of vertices, which is 3 plus 1. And then doing some manipulation, you can easily show that the number of vertices and number of edges in the Voronoi diagram are order of n. So it's very clear that you are constructing order of n square perpendicular bisector, by which you can construct order n square vertices, you can construct order n square vertices and segments, but not all those intersections and those segments finally become the Voronoi edge or Voronoi vertex. So what makes Voronoi vertex different from just another intersection? So there's a theorem which says a point V is a Voronoi vertex if and only if there exists a circle centered at V with 3 or more sides on its boundary and none its interior. So this V will be a vertex. It means there are 3 Voronoi cells which meet here. So there will be 3 sides equidistant, at least 3 sides equidistant from this. So you can make a circle centered at V passing through these sides. Moreover, there can't be any side inside the circle. Why? Because suppose if there is a side inside, then this point V can't be a vertex because it will be closest to this side and it should belong to the Voronoi cell of that side. Similarly, there is also a theorem for Voronoi edge which says that E is a Voronoi edge if and only if for every point x on the edge, the circle centered at x passes through just 2 sides and with no side in its interior. So since all the points on the edge are equidistant from these 2 sides, so you should be able to make a circle centered on x and passing through the side. And again with the same reason that there can't be any point in the inside, because if it is, then this can't be an edge. This should belong to the Voronoi cell of that side. So our naive method, which is conceptually very simple, but it's evident now that it's not efficient, and we need a better algorithm to construct Voronoi diagrams, and this is where brilliance steps in with Fortune's elegant sweep-line algorithm.
So yeah, I'll be explaining the Fortune sweep-line algorithm. Clearly we saw we were doing so much of stuff using n square intersections to just get O of n edges and vertices. So that was like 2n equations. The Fortune sweep-line algorithm is based on a classic computational geometric paradigm called as the sweep-line paradigm. What is the general approach is that in a sweep-line paradigm, what we do here is that we have our sides, we take a horizontal line and we sweep the line from the top to bottom and incrementally construct our Voronoi diagram as the line goes down. So I have my sides and I have a sweep line. First, I just see all the sides above the sweep line and I construct the Voronoi diagram based on just these sides, and I move my line down, which will interact, new sides will come, and I modify my Voronoi diagram. So incrementally as I move my line down, the Voronoi diagram gets built. So imagine this like a window slide or a curtain. You pull it down and the Voronoi diagram slowly, gradually gets built. But is it that easy though? The main problem with the classic sweep-line paradigm is that when you deal with the sides above and you construct a Voronoi diagram based on these sides, you have no information about the sides below as of now. But the problem is that the sides below will disturb the region above as well. For example, this point here belongs to this side, but your sweep line is here and you construct a Voronoi diagram based on these sides. So you would have allocated this point to some side here in a wrong way, and you sweep your line down, the points from the below will come. Now you have to reconstruct or completely modify your Voronoi construction line. That's bad. Ideally we want something like, I have my sweep line, I have sides, I construct some part of the Voronoi diagram, and as I pull my sweep line down, as I add sides, I just add Voronoi cells without disturbing the ones that I've created already. That is more efficient. And this is where Stephen Fortune's genius way of thinking comes. Instead of maintaining the classic sweep line, he maintains a beautiful parabolic arc called as a beach line. So, what do? The idea is, we construct the parts of the Warnai diagram that won't get affected by the sides below. So, when I pull my sweep line down, when the sides come, the already initially constructed Warnai cells won't get affected. So, I'm not going to modify or recompute anything. And I'm going to pull my sweep line down and everything will get constructed incrementally without wasting my previous computations. How will I do that? I will consider the region above the sweep line such that if I take a point, I take the region of set of all points that is closer to the closest side than the sweep line. Why? If a point is closer to the closest side than the sweep line, since all the sides are below the sweep line, this point is far away from all the sides when compared to the sides here. So for a fact, indeed, this point will belong to some side here, some cell here. So even when I move my sweep line down, these cells of these sides are not going to interfere with that. So I am certain about few points that follow this special property that they are closer to some closest side above than the sweep line. And if I bound the region of all points, I will get a parabolic arc. I will get a beautiful wavy line called as the beach line. Why a parabolic arc? We know that locus of all points that is equidistant from a point and a line is a parabola. The point is the focus and the line is the directrix, right? So similarly, every side here will contribute a parabola. Every side is a focus and the sweep line is the directrix. So we have parabolic arcs. Every side will give a parabola and we take the lowest of it. So for all the points above, that is going to be enclosed within a parabola. So that is going to be closer to the closest side than the sweep line. So I'm certain about these points. So the brilliant idea is that instead of moving the sweep line down, I will sweep the beach line down and somehow incrementally construct the Warnai line. So beach line, fine. How exactly and how is it going to be useful? This parabolic arc has so much of information about the Warnai diagram. How exactly? Let's look at these special points called as the break points. What are they? The intersection of parabolas, and all the break points are always equidistant from two sides. Why? Because they belong to two parabolas. So they are equidistant from two focus and the sweep line and the directrix. So they are equidistant from two sides. So these break points belong to the edges. And as I move my sweep line down, my sides are fixed, focus is fixed, but directrix is moving. So the parabola will grow and the break points will also go down. But at every instance, these break points will belong to the edge. So when I move my sweep line down, I'm basically tracing out my edges. My beach line moves down, my break points moves down, and every instant they belong to the edge. So basically I'll be able to find the edge. So that powerful beach line is. And another property is that sometimes the parabolas tend to shrink. The middle parabolas tend to shrink. Why? Intuitively we know the break points trace the edge. If two edges converge to a vertex, the parabola is going to go smaller, and converge into a vertex. The break points will converge into a vertex. So, my beach line gives a lot of details about the edges and the vertex. And what is even constructing a Warnai diagram? It's basically telling where the edges are and where the vertices are. And if I am able to get where the edges are and the vertices are by just maintaining a beach line, I am so good at it. And now the problem is, how exactly will I maintain the beach line? The beach line, the parabolic arc function, is just an abstract thing. Nowhere in my algorithm should I construct the parabola. I'm just going to, it is never going to exist. It's just a conceptual thing. And we just track how it's combinatorially going to change. It can change only when a new parabola gets added or parabola gets shrinks. When does a new parabola get added? It happens on an event called as the site event. What is it? When I pull my sweep line down and a sweep line intersects with a new site below. Since all sides contribute one parabola, since I have added a new site here, this will contribute a new parabola. But this will be a degenerate parabola. What do I mean? The focus and the directrix are at distance 0 at this point, so the width of the parabola will be 0. But eventually, as I pull my sweep line down, the directrix and the focus distance will increase and the parabola will start to grow. Note one thing, I have had a new 2 breakpoints here at every site event. So, at a site event, new 2 breakpoints form, and as I pull them, the breakpoints start growing. They go and they trace a new edge. So, what do I know? In a site event, a new arc is added to my beach line and a new edge gets to be traced in my worn line diagram. And also there is a theorem that this is the only way in which arc can be added. There is a very good proof by contradiction in Mark D. Burke's Computational Geometry and Applications book. I suggest you to do a follow-up reading in that. And as the circle event which I already discussed, a parabola shrinks and we get a vertex. Why is it a vertex? This satisfies that empty circle property. We'll not go into the proof, but then we intuitively get the idea that every circle event, whenever a parabola shrinks, we get a vertex. Every circle event is going to give me a vertex. And by a theorem, again, for which I refer you the proof in Mark D. Burke's, every vertex is captured by a circle event. So, just by maintaining the beach line, how it changes, I know where exactly a vertex will come and where exactly the edges will start. That exactly is what is Fortune's algorithm. And we need a few data structures to effectively implement this, but I'm not going to go into the details of data structures as the talk should be short. But just assume that you have some fancy data structures to represent my worn line diagram. I'll just call it doubly linked list. What does it do? It has the set of edges and it somehow stores the set of vertices. And I store my beach line in a balanced binary. How exactly? Let's not go into the details, but to give you a rough idea, I'll have my balanced binary tree and the leaf nodes are the ones that are going to represent my parabolic arcs. As I told, the beach line is never actually existing. We just have a representation of it. So the node that creates the parabolic arc is stored here. So Pi corresponds to this parabolic arc. Similarly, this parabolic arc there, so we have the leaf nodes and the internal nodes have the denotation for the breakpoints. So, and we also have something called as the queue. What does it do? It stores the list of events in the order of their y coordinates. What do I mean? Site events. What are site events? When my sweep line meets a site. And I know exactly where these will happen because in my input I am given the end site points. I have been asked to construct a worn line diagram given the end points. So I'll have a queue. I'll put all my site points in from top to bottom. And I'll put my circle events. I can find out where exactly my parabolas will converge and I'll add them to the queue. How exactly? I'll tell you. So, if you have a queue of events, I'm sweeping my line from the top to bottom, which means what? I'm going to the queue and seeing it from the top to bottom, event by event, and I'll handle every event specifically. How do I handle every event? So, the algorithm is just the same what I told. You have a queue, event by event, you sweep the line top to bottom. Basically, you go to the queue, one by one you go down, and for every event, you handle it properly. That is, you add a corresponding edge in the worn line diagram, you make changes to the binary tree, and how do you do it? Now, when you have a site event, two things is that a new edge starts getting traced. So, you go to your doubly linked list that represents my worn line diagram, and I add an edge here. And a new parabola is inserted or it breaks the existing beach line. So what do? I go to my beach line and I insert a new node. And we do a few more things which I'll come back to you later. And next we talk about the circle event. So we know where the site events are going to be because they are given as an input, but we don't know where the breakpoints will converge because and we have to find it. I told that we will find it on the fly. How do you do it? During a site event, a new parabola gets added. So now we have three consecutive parabolas, three sets of consecutive parabolas. these can potentially converge or not converge. Basically the breakpoints can converge or not converge. How do you find it? You have three parabolas, you have three sides. Just find the circle or the intersection of all their perpendicular bisectors. If they intersect below, that means the perpendicular bisectors are what? Basically the edges. If the perpendicular bisectors intersect below, the edges are intersecting below. These two edges are going to intersect below. Means they will converge. Means there will be a vertex. And that's fine. Like you have three sides for which you have x and y. You find the circumcircle and find the circumcenter. If it's below, then you know that there's going to be a circle event happening. And you know where exactly will it happen. You know the y coordinate. So after a site event, you check for potential circle events. And if there is a circle event, you know the y coordinate. So you put that in your queue now. So you start off with a queue of site events, you went to one by one of the sites, you added parabolas and you check if they are converging or not, and if they are converging, then you get where exactly they will happen and you plug in the circle events in the queue. So when you sweep down again, you will get a site event or a circle event. Now you will handle a circle event. If it's a circle event or site event, you will do the same thing. How do you handle a circle event? So in a circle event, what should you do? A parabolic arc is going to disappear. So go to the balanced binary tree, delete the node. And let's say this parabolic arc is going to disappear. And after they disappear, these two parabolas start to intersect. A new breakpoint is formed. What does that mean? A new edge is going to be traced because a breakpoint traces an edge always. So now you add in your Warner diagram the new edge. You know where exactly the edge is, you know the breakpoints because you have the binary representation tree that has the breakpoints and the nodes. And since this parabola is disappearing, you go to the corresponding node, delete that from the binary tree. One more thing you have to do is, since two new parabolas have started to intersect, now for these three parabolas, you haven't checked their potential circle event. That is, you don't know if they will converge or not. So you do the same test and check if they converge. If they converge, go to the queue and add them as a site event again. So it's that. So there's one more thing. There's something called as a false alarm. When you see if three parabolas are going to converge or not, and you go, let's say that the breakpoint converges somewhere way below, and then you add it to the queue. But then before even reaching that, you pulled your sweep line down and you got a side point. And these three parabolas which were supposed to converge now got broken. So a new parabola got added. So this arc is broken into two. There are breakpoints now. So the parabolas that were supposed to converge won't converge because this parabola is not going to exist at all. But then you have a circle event down. What do? When you add a site event is the only way that will disturb this parabola, right? So when you have a site event, if this is breaking something, you go and delete the circle event. How? In your balanced binary tree, in the nodes, you just don't store the node. Don't store the node representing the parabolic arc. You store a pointer as well, which corresponds to if there is a circle event. So what do? You get a site event, go to the balanced binary tree, do a search, find the parabolic arc up. If there exists an arc, you will get a node and check if the node has a pointer to a circle event. If that has, then that's a false alarm. You have to go back to that y coordinate in the queue and then delete the circle event again. So the main idea is that beach line and the sweeping algorithm is like too elegant, and the beach line gives you a lot of information, and just you have to be brilliant about how to maintain it effectively. I have been given the site points and I'm just going to track how my beach lines will change with the site events. And that's it. I have constructed all the one eye vertices and all the one eye edges in so much elegance. There's a simulation for this, you can look into it. I can give you my slides and you can click this and it will direct you. So coming to the complexity, okay, there will be O of n site events because there are endpoints. How many circle events will be there? There will be O of n circle events. Why? Every circle event is going to capture a vertex, and she just proved that the number of vertices is O of n, so there's going to be O of n circle event. And what do I do in each site event or circle event? I'm just going to go to my balanced binary tree and I'm going to add a node inside a node or delete a node, which is going to be of log n. So there are n, O of n things I have to do, and at each time I'm just going to do an operation of log n. So my Fortune's algorithm is order of complexity n log n. We came from an m square log n to an n log n. Is this the most optimal way though? I leave it as a food for thought with a fun fact that solving the problem of sorting of n numbers is equivalent to constructing the Warnai diagram of n points. I am not going to go into the detail, but this is an amazing thing which we all should follow up and discuss on. So there are more applications to Warnai diagrams, like this is a robot and there's a motion plan into it, but I don't want to do the applications because of the time. I'll just leave you all with another food for thought. Isn't this more a practical or a fundamental question that, let's say we have a city and that we have already divided into regions, and now we have to find where exactly should I place my post office so that all these regions, the closest post office is here. I mean, given the cells already, can I construct the side points? Initially we discussed, given the side points, let's divide the city into cells. Now I'm telling, we have already the cities and already the map. I just want to know where exactly should I build my post office. But given the cells, where should I construct my side points? I am not going to answer that question because that's called the inverse Warnai problem, and that's an NP hard problem, and I have no clue how to even deal with NP hard problems. So, but that's a very great exercise and follow-up we should all read upon, and yeah, that is some geometric beauty today I wanted to share with all of you. And the slides are edited from someone else's slides and all the credits have been given, and these are the two books which helped me a lot to learn about these things. Thank you very much. Yeah.
So how does like the computational cost of this making the Warnai diagram scale with dimension? You're talking about 2 dimensions.
Oh yeah. So you can extend the Warnai diagrams to 3D as well, and I don't know the details of how you construct a Warnai cell in 3-dimensional, but there is a clear extension from planars to
Plain street, not line street. You do that, it works. Anyway,
I'm not sure of the time complexity of that. For a fact, we construct Warnai diagrams with side points, and there's something we can given line segments instead of side points, we can construct a similarly defined Warnai cell. But I'm not sure of the complexities and stuff.
Okay.
But there is an extension, that's what. Any other questions, please? Okay, thank you so much.
Thank you, Archana and Ramnath, for that presentation. Now we'll disperse for lunch and we'll come back at 1:50 for the talk by Professor Arindam Khan. Thank you. Now, we are delighted to welcome Professor Arindam Khan, a leading researcher at the Department of Computer Science and Automation, IISc. Please join me in welcoming him as he takes us through the intersection of algorithms, randomness, and geometry.
You can use this mic. Or this one. This is the mic, right?
No, this is for the streaming.
Okay.
This one also works.
Okay. Thank you everyone, and thank you to the organizers for inviting me for this talk. So this talk is about life, which lies at the intersection of algorithms, randomness, and geometry. Let me explain. So life revolves around three things. One is things, objects, uncertainty, and processes. Things are geometric in nature, rectangular shapes, or sometimes they are spheres, torus, cones, and other objects. And then we have uncertainty in real life, in quantum mechanics, or in stock markets, or even with grading. You have bell curves there. And to deal with these things and uncertainty, we learn processes, sometimes by reading books, sometimes doing trial and error methods, and then sometimes by building. And if we talk about anything, I can put them at the intersection of these three things. Think of ML. What is ML? ML is the intersection of three things again: algorithms, high dimensional geometry, and randomness. So algorithms like linear regression, logistic regression, they're just algorithms which are used in machine learning. Randomness like sampling, Bayesian methods, concentration used in machine learning. And then you have VC dimension, code sets, high dimensional geometry. Again, you're dealing with large data, you're learning from that. So both sampling, randomness, as well as geometry, both are important. In general, if you take computer science, again I can tell the same. There are different algorithmic paradigms like approximation, online, dynamic, streaming, parameterized, fine-grained, different paradigms. And there are different techniques which we learn in algorithms to deal with this, the problem that we solve: dynamic programming, linear programming, divide and conquer, local search. Randomness, we have application in computer science in cryptography, Monte Carlo method, randomized algorithms. And there are Charnoff-Hofding concentration inequality, random walk, sketching, sampling, random graphs. There are many techniques which we use from randomness to get improved algorithms. And geometry, from computational geometry and data structures, robotics, computer vision, geometry is also omnipresent. And there are techniques like convex hull, packing, covering, Voronoi diagram, range searching are very critical to many of these applications. Now, as many of you are students from maths and computing batch, this is the question I'll start with. What came first, math or computing? It was asked by Mose Vardi. He is a professor in Rice University. And according to him, it's both. So this is the first known mathematical artifact called Lebombo bone. It's found near Swaziland. There is a mountain called Lebombo Mountains. It's a tally stick. So there are some inscriptions. There are 29 inscriptions. So this was used as a counting object. Probably it was counting the number of the days in the lunar phase. So this was the first known mathematical artifact which is just counting. And one can also claim that counting is also a primitive kind of computing. So in a way, his claim is neither math or nor computing. Neither of them came first. They came together. Both were developed by humans as a way to reason about our physical world, and they are intertwined for last 40 years, and they will continue. So that also tells you about the relevance of maths and computing programs. And there are some other examples which are more mathematical in nature for algorithms. This is Sumerian multiplication table, and they had some primitive algorithms how to multiply two numbers. And the right side we have papyrus fragment from Euclid's Element, which was dealing with geometry, but also it talks about first algorithm. We'll come to that later. In ancient India also, the treatment of mathematics was very procedural in nature or algorithmic in nature. So in this example by Sulba Sutras, there are geometric algorithms by Bodhayana, Apastamba, Katyayana who gave procedures for bisecting lines, drawing perpendiculars, constructing squares and rectangles. And then there are primitive notions of computer science like recursion and divided conquer, were already there in the work of Pingala. So there is a book called Chanda Shastra. I also have a YouTube channel called Algorithm. There I talk about this Chanda Shastra, how this is connected with dynamic programming, how the ideas of how Pingala came up with binary numbers, how Hemachandra and others came up with the idea of recursion and basic dynamic programming. Now, let me again start with this question, what is computer science? And there are two schools of thoughts. So one is by Newell, Parlis and Simon, and all of them are Turing Award winners, the top prize in computer science. According to them, CS is the study of computers and related phenomena like algorithms. And then the other class of thought, where I also agree with, is by the father of analysis of algorithms, Donald Knuth, another Turing Award winner, and he says computer science is the study of algorithms and related phenomena such as computers. And that's crucial because what makes us computer scientists is the way we think. That's the algorithmic thinking. And that's kind of distinguishing a computer scientist from other disciplines. And by the way, if you are interested about Donald Knuth, then there is a book called The Art of Computer Programming written by him. So have a look at it. Look at it, and there is a quote by Bill Gates that if you have read Art of Computing, send me an email, then I will look at your CV. It's a really long and very comprehensive treatment of algorithm. So algorithm can be thought as a spirit of computing. It's a core of computer science, and the algorithmic lens is transforming not only computer science but all areas of science. So think of math. There are multiple breakthroughs in math, like Cadison-Singer theorem, were made by computer scientists. Physics, quantum computing, Shor's algorithm, they are again done by computer scientists. Economics Nobel Prize winner like Shapley, Gale, their work, I think only Shapley and Roth got, but their work on stable matching, the algorithm called deferred acceptance on Nobel Prize, that's also again computer science algorithmic work. So this computer science is omnipresent nowadays. Let me also mention the connection between algorithm and India further. So this is Al-Khwarizmi, and the name algorithm came from his name. So he wrote a book called Kitab al-Hisab al-Hindi. As you can see, Kitab means book, Hisab means calculations, Hindi Indian. So it's basically the way of Indian mathematics. And this book was instrumental in spreading the Hindu-Arabic numeral systems through Europe, through Middle East and Europe. And this was very procedural, unlike Greek mathematics, which was proof-based. This was very algorithmic or procedural in nature. And this book name in Latin was Algorithmi de Numero Indorum, and algorithmy is the name of Al-Khwarizmi in Latin, and from that the way of mathematics, this kind of procedural mathematics, got the name algorithms. Now we talked about algorithms and we are trying to solve optimization questions using algorithms, but many times they are very hard, and sometimes the hardness comes from the computational hardness, like NP hardness. For example, for many problems we don't know how to find quickly the correct solution for the problem. Think of how can we color a graph with minimum colors, can we find optimal schedule of some jobs, can we find the longest path in a graph, and so on. Then there could be other ways in which we can get more hardness, for example uncertainty. Many times you don't have the entire data and still you have to take a decision. For example, should I marry this person? So there is a problem called secretary problem, which we'll see, which kind of answers not completely. Or should I buy the stock? There is a multiplicative weight update algorithm or online learning which deals with these kind of questions. Okay, got to the next slide already. Yeah. But then we have algorithms to conquer. There are approximation algorithms. So if you have NP-hard problem, you may not get the exact solution quickly, but you can still find a efficient approximate solution, which is good enough in many practical problems. And then if you don't have complete input, then you have online algorithms. And example of online algorithms, for example, when you book cabs in Uber or Ola, sometimes the cab needs to be assigned and you don't know what are the future requests. So this kind of algorithms are also very critical, or ad allocation problems which are used by Google and others for their main revenue. That's again some kind of online algorithms. So let me just define approximation, but many of you have already taken, I think, DA, so you already know, but still, it just says that for many problems, NP-HAT problems especially, we don't have any algorithm that has three things together. We want to find the optimal solution for all instances, and it should be efficient in polynomial time. So in practice, we are fine if it is, let's say, within 5%, 10%, 15%, or even 5 times the optimal solution, depending on the situation. The approximation algorithm relaxes the first constraint that we are fine with near optimal solution, but we want it to be polynomial time, and it should work for all instances. And the definition of approximation says that a minimization problem A, for a minimization problem algorithm A is alpha approximation if for any input instance I, the value of the solution returned by the algorithm AI, is less than equal to alpha times the value of the optimal solution for that instance. So the worst case ratio of your algorithm solution and optimal solution, that is known to be the approximation ratio. And for online case, the same notion is known as competitive ratio. So we'll see some examples of approximation online, but let me go to the next part, which is how randomness can help in algorithms. Now randomness roughly means lack of certainty. You don't know what is going to happen next, like coin toss. And this is a kind of old slide. So at that time India lost 12 consecutive tosses, but today I think the number is 18. So even today there is Australia-India match, again India lost the toss. So it's 18 consecutive tosses that India has lost. So what is the probability of this? So if we think the coin is balanced with probability half, let's say we'll win. So consecutively 18 times you lose is 1 by 2 to the power 18, which is very, very small. And it's kind of counterintuitive that you might think, okay, now we have lost 18 times, that means next time we'll surely win. That may not be true. That's called gambler fallacy. That if a coin has landed, let's say 18 times in a row, it is due to land tails, but that is not true. Each flip is independent, so it's still 50-50 to win, which is counterintuitive. But there is still some structure. So this is a statistics from toss win percentages in, this one is 1 day, this is test, this is T20. And these are all captains who have captained at least 125 matches. And this is the percentage of tosses that they have won. So if you see, in case of this is 1 day, most successful captain in terms of winning percentage in toss is Muhammad Azharuddin, who won 55%, and worst is Brian Lara, 45%. And the similar stories for other two cases. So though there is no certainty, there is still some structure that if we toss a coin multiple times, it roughly reaches a 45 to 55% range. And though this is not certain, this is dominating our real life. Think of subparticle physics, Brownian motion, radioactive decay, all these are random events. Or in biology, mutation and evolution, they're again some random event. Economics, price fluctuation in free market economy, it's random. And there is another thesis by this F. N. David, he's a historian, and according to him, the first invention of humans are some gambling device. This is called talus, these objects. And in Sumeria, already it was found, they are tetrahedral in nature, and they are using, there are 4 sides, and you can toss it and then it lands, and based on that you tell fortune. So that's kind of the first invention according to him. But though already gambling was quite popular, the formal notion of probability came quite late, and one might ask why even Greeks, like who were doing math, or Indians, they were math for last 2000, 3000 years, yes, why people did not come up with the idea of probability. One reason is counterintuitive. Gambling already had a negative connotation, and in Greece, for example, this is Fortuna, Lady Luck, she is blind, and Sapientia, the Lady of Wisdom, she is omniscient and she knows everything. And the Greeks thought the science is about causes, not chance. So chance is something which is not very scientific. It's more some heuristic artifact, and they believed in perfect math, everything should be proven from some set of axioms, and those probability, chance did not fit into that kind of framework. But in India also there is some notion of probability. So in Mahabharata there is a story of Nala, and there I can tell a story later in detail, but they mention somehow connect sampling with the game of dice, which was interesting. And this is the game called Mokshapatnam, or Snake and Ladder, There again, it shows kind of life is random, and sometimes randomness will take you to, I don't know, the ladder. Sometimes it can lead you to the tail of the snake. So there was some initial notion of probability, and there are multiple books which talks about these things and how some initial notion of probability was there, but it was not very rigorous, or there was no foundational constructs in the study of probability at that point. Let me also mention some more counterintuitive nature of randomness. We are playing a game, and there is a person, you have to guess his or her birthday. Now if it's a random, you have only one chance, and then if you guess it correctly, then you get 100 crore. You guess it incorrectly, you pay 1 lakh. Now, how many of you will play this game? Mostly no, because it's risky. You might lose 1 lakh. But let's say if I make it deterministic, that okay, I give you 366 chances, then you will play, because then out of 366 different chances, in one case you'll surely get to the right birthday, and then you will gain. But if I tell you, okay, I'll give you 366 random chances, then probably you'll still think maybe I'll not play. So that's why in human way of reasoning, it's very counterintuitive. That's another example. So I have 3 ways to travel. In one case, I am going from Bangalore to Bombay by flight, which is 600 miles. In other case, I am going just from here to Malleshwaram by bike, which is 1 mile. And third case, from IISc to MG Road, which is 10 miles. Which one is safer? By safer, I mean which has less chance of dying. How many of you think is first one? How many of you think second option? How many of you think last option? Okay. As you have already studied probability, maybe many of you know. So actually, for 1 billion miles, death cases in air travel is 0.07, car is 8, and bike is 230. So if we take into the distances, which are larger in this case, it still shows the ratio that by traveling by this amount by flight, it's if it is the ratio is like 1:5:2. It's much safer to travel by flight. It's again counterintuitive. This is another example of birthday paradox, which is very counterintuitive. It says that what is the probability that there are 2 people in India who know each other, but they are not siblings or cousins. They have the same birthday. Okay, and let's say they are also not spouses. So they have the same birthday. Their fathers have the same birthday. Their mothers have the same birthday, and their spouses have the same birthday. It's very unlikely event, right? But what is the probability of this? Any guess? 1%, 0.1%, 90%. Any guess? 90%. Huh? So it's actually 99.8%. And there is a law, the phenomena of law of truly large numbers by Diaconis and Mosler. So when enormous number of events and people and their interactions accumulate over time, almost any outrageous event is bound to occur. This is one example. So some other stories about birthday paradox. So there was this Canadian, you don't have to read this entire thing, but the story is, in Canada there was a company, and they had 2.4 million customers who bought cars from the company. So they were giving 500 automobiles from that, it's not company, some lottery company, and they were giving 50 automobiles as a gift to this 2.4 million subscribers. So they were randomly choose 500 people from 2.4 million and give them cars. And the way they are doing is they are just picking one random number out of 2.44 million, and that particular person will get the car. And they just gave, just by sampling 500 times, they found one single person on 2 times, the same person on two cars. Initially, they thought it might be a glitch in the random number generator, but then it turns out just the birthday paradox that if you have n people, roughly, if you have root n number, if you have root n people in the room and there are n possible, let's say, birthdays, then with half probability you will find a clash. And this is another paradox, famous paradox called Monty Hall paradox. I will not talk details about this, but this is about some game show, and you can Google search about the paradox and you will learn about this. But it is so counterintuitive that even a famous mathematician, Paul Adosh, he fumbled on this, and he did not believe the proof that the other person provided. And only after we coded and showed him the program, and then he realized, okay, this is really correct. So even mathematicians sometimes get confused with these paradoxes in probability. And it's another paradox. Again, I will not go to the details of the paradox, but it roughly says there are two cricket players, Rohit Sharma and Virat Kohli, and in 2 consecutive years, Rohit Sharma's average is better than Kohli. Then can it be the case that the cumulative average of Rohit Sharma is less than Kohli? So in each individual year, one person is better than the other in 2 years, but then you take the sum of the 2 years, then the other person gets better. And that's called Simpson's paradox, and there is one example from real life example from baseball, where there is a player who had better average in both the years, but the combined average is better for the other player if you take the 2 years. Okay, so with the background in randomness, how can they help in algorithms? So let's ask a simple question that given an array, we have n distinct integers, and our goal is to return an integer which is larger than the median of the array. So median is basically the n by 2th largest number of the array. So many of you are smiling because I already told this example maybe a couple of times to you. So the goal is do it as fast as possible. So one trivial solution will be probably just sort, find the median and done, but that's n log n time. Other option is probably you can read the entire array and you reach n by 2 plus 1 and take the best highest number among this n by 2 plus 1, and that is surely more than the median number, but that takes n by 2 number of reads. And one can show any deterministic algorithm you will need n by 2 reading. But can randomness help? So here the algorithm is you sample 100 times independently uniformly at random and return the maximum. So then with probability half, any sample number is smaller than the median. With probability 2 to the power minus 100, all sample numbers are smaller than median, and with probability almost 1, the return number is larger than the median. So think of n is very very large, 10 to the power 20. Then in the deterministic case you have to read 10 to the power 20 by 2. But in randomized case you can actually run only for 100 numbers, and then with probability almost 1 you will achieve success. So that's the power of randomness. Okay. So now I will talk about the problem, like whom to marry, this famous problem called secretary problem. So there are m candidates and they arrive one by one, and let's say Jasmine, she wants to marry, and there are 4 candidates, but she does not know the values a priori. So they arrive one by one, and once they arrive you get to see their value, and based on their value you either select or you reject. If you select, you marry that person, and if you reject, you can continue, and your goal is to select the best match. You can again show if it is deterministic, then it's hopeless. You with very small probability you will find the best match. But then what you can do, because there is an adversary, the adversary can choose the candidates as well as their arrival order. But if I randomly permute the candidates, I don't know their values, but I just don't let the adversary pick up his or her arrival order, and then call the candidates one by one. And then what we do is we remember the first n by e candidates. So let's say first 37% of the candidate, and we reject all of them, but we remember the best among these people. And then whoever comes better than that particular value, we accept that person. So if you have 100 people, first 37 people you reject, but you remember who is the best among these 37. And next, if someone comes who are better than this person, you accept that person. And it turns out this is the optimal strategy. This is the optimal strategy, and with probability 1 by e, you will find the best candidate by this strategy. This is called secretary problem, and there are many many applications of this in optimal shopping time and algorithms. I will briefly talk about one result of mine last SODA, which was about a problem called bin packing problem. As I have less time, I will just go over very quickly about the problem definition, but I will be happy to talk more about these problems. And I also have, I think, talk on my webpage. So in bin packing, you have a bunch of items. Let's say each item has some value between 0 to 1. And you have to pack the items into some minimum number of bins, which has capacity 1. So it's a partitioning kind of a question. I will not go into detail about this problem, but it has many applications, and there are multiple Turing award winners from Andy Yao to Ullman, Richard Karp. They have worked on this problem and showed. And it has many applications in cloud computing, smart grids, logistics. So one big open question here is, what is the best practical algorithm for bin packing? And there is a conjecture by Kenyan around 30 years back that the best simple algorithm is you randomly permute the items that you want to pack and then apply something called best fit. So you take the item and among all the bins that are open, whatever bin fits is best, that means after packing the item the amount of waste space is least you pack the item in that bin. And it's called best fit. Again, I am not going to details, but this is the conjecture, this is the best practical algorithm, and the conjecture is that you should get something like 1.144 ratio for this algorithm. And she provided an upper bound of 1.5 and lower bound of 1.08 for this algorithm, the competitive ratio or approximation ratio for this algorithm. But there was no progress in last 3 decades. What we did with one undergrad from IISc, Anish Hebbar, and one of my students, KV and Srinivas, PhD student, we slightly improved it. So from 1.08 we got 1.144, which was the conjectured value, and then from 1.5 we showed it's 1.5 minus 10 to the power minus 9. But it's still a big breakthrough because of 10 to the power minus 9. And though it looks very trivial, the improvement, it actually requires a lot of math and things from probability theory, Markov chains and stuff comes into this. So if you're interested, again I can talk about this in detail, but it's a very complicated paper, so it will take an hour at least to talk about the basics of this algorithm, the analysis. Okay, so the last part of my talk was about geometry. So we covered algorithms, randomness, and now geometry. Now neuroscientists were studying, it's an article from New York Times, that is geometry a language? So what makes our species intelligent? And what differentiates human intelligence from, let's say, chimpanzees and other animals? And they found probably it is the shapes or geometry. The way we recognize shapes is kind of unique to humans. So for example, all the shapes that we like, flag, money, all these are rectangular in shape. But in nature you will not find, even in this room, you think of this board, computer, all these things are rectangular or window, door, they're rectangular in nature. But I mean, in nature you will not find rectangles, you will find maybe spheres or maybe lines, but not rectangles. And if you find rectangles in nature, it becomes a news. Like this was an iceberg, it does not look like a rectangle, but somehow it looks like somewhat like rectangle. It was a news that okay, rectangular iceberg spotted, and there was some conspiracy theory, this probably aliens who made these rectangles, etc., etc. So it's very unlikely in nature you will find rectangles. And there are these arts by Joseph Albers, and all these arts are like this. You have squares inside squares inside squares, and they're different colors, and they are like $1 million or $10 million worth. So, and he was asked that why do you use squares for your paintings? So he says that I still like to believe that square is a human invention, and that tickles me. So when I have a preference for it, then I can only say excuse me. So that's his homage to the square. Now geometry was already studied in Greece long time back by Euclid in his book Elements, as I mentioned earlier as well. And they presented geometry in an ideal axiomatic form based on deductive proofs. But they also had some algorithms. For example, Euclid's GCD algorithm, that's actually given the geometric way. So the algorithm is geometrical. The GCD is basically the two lengths A and B, and then the GCD of the lengths are correspond to the greatest length G that measures A and B evenly. That was the definition of GCD, and it was a geometric algorithm in this book. In geometry, in India as well, this played a huge role. So this is basically Shulva Sutra from slopes, which mentions how to create a diagonal or some geometric constructions are given. And then in Vedic art, a lot of constructions are there, geometric construction, triangle, etc. They are using geometry to create this object. And though it was more like a ritual, it required a lot of steps to create these geometric constructions, which led to a lot of sutras, which gave how to find area preserving transformation from one geometric shape to other shapes, how to transform the square to a triangle or rectangle, and so on. And recently, geometry, the best place to do in India is IISc. So this is a geometry workshop which we had in last year, and this is the workshop people, and the top people from all over the world, they came, And in fact, the top conference in geometry is SOCG, Symposium on Geometric Algorithms. We are going to have it in IISc in 2027. So most of you are probably here. So if you're going to be volunteer for SOCG 2027, let me know. And these are textbook of geometry written by Mark DeBerg et al. And Mark DeBerg is coming here for 6 months next year. So again, a great chance for you to work. And another person is Tamalde, who is also an IISc alumnus. He will again be coming here next year or next to next year in his sabbatical. So it's a great opportunity for us to learn geometry from them. Okay, let me now mention this slide, something happened, but let me just mention about this result in iCalc last year. So this is again a question from sphere packing, which was studied by Kepler. And this says that, okay, if you go to market, there are sellers which sells oranges. What is the optimal way of arranging this oranges such that the amount of space used is the least? So he proposed some way of packing which he saw in the market in 1611, but then only in 2 dimension that was proven by Lagrange for some variant in 1773. And then only in 2012 we got a proof in 3 dimensions. So Lagrange gave 2-dimensional proof in 3 dimension. And in other dimension it was open only in 2019. Marina Vyazovska, she is a Ukrainian mathematician. She solved it for dimension 8 and 24 and she got Fields medal. So it's such an important problem. So we were looking at this from an algorithmic point of view. So we are given bunch of disks in 2 dimension or in 3 dimension spheres, and each sphere has some, or disk has some associated profit. And then your goal is to pack them in a unit square knapsack. So the goal is to pack a subset of these spheres which can fit non-overlapping. So in this case, none of them are overlapping within this square knapsack, and you have to maximize the amount of profit of these packed items. And an APITAS, which is the kind of the best approximation that you can get, let's say 1.001, was open for this problem for a long time, and we showed that it is possible to get APITAS for these objects, not only for 2 dimensions but for any constant dimensions. Let me also mention a couple of more recent results and 2 interesting problems. One is called 3D knapsack, one is called 3D bin packing. So first question, let's say you are packing to some exotic location for a vacation, let's say in Lakshadweep, and you have many things to pack, but in the airlines you can only carry 1 suitcase, and there are some restrictions. You have limited space, so you can probably use only a 4 feet by 3 feet kind of a suitcase. So how do you pack a subset of items such that you maximize your profit? So some items are very important, let's say sunscreen or summer clothes, etc. And some items, winter jackets, are not really useful in that case. So how do you decide which items to pack, and you have to maximize the amount of profit? So that question is called 3D knapsack intuitively. And the other question is, let's say you got a job or you're traveling to IISc once you got the admission, and you have many things to pack, and you have to pack all of the things. But then you might want to use multiple suitcases. You can probably transport them via truck. So now your goal is to pack all items into minimum number of boxes. This is called bin packing. So both bin packing and knapsack are very fundamental question. And this year we had couple of interesting results. In 3-dimensional case, when items are cuboids in nature, in 3D knapsack we gave a 4.78 approximation, which gave an improvement after 18 years. And for 3D bin packing, we gave a 6 approximation, which improved after 35 years. Now in the remaining 5 minutes, I will also talk about, last I was talking about how probability was so counterintuitive. Now I will talk about how geometry can be counterintuitive. So think of this example in 2 dimensions. So I am given a square of side length 4, and I give you 4 squares, 4 discs, unit discs. So they have unit radius, and I pack them in the corner. And then in the middle portion, there is some empty space. I want to pack a small disc here. So in 2 dimensions, what is the radius of this particular disc? If you think of it, you will realize that this distance from this point to here is like root 1 plus 1, which is 2, square root 2, and this is 1. So it's square root 2 minus 1, which is 0.41. That is the distance. So one can show, if I have n-dimensional objects, what I do is all the corners I try to fill with unit balls, and in d dimension unit balls, and after placing them, whatever is left in that region I want to place a ball of as large a radius as possible. And if you do the calculation, you will realize in dimension d or dimension n, the radius of the inner ball is root n minus 1. In 2 dimensions it's root 2 minus 1, but the same calculations will go and you will get root n minus 1. So for 2 dimensions the value is 0.41, which is fine. This is 1, this is 0.41, much smaller than 1. 3.7341, so it becomes very large, and then it goes outside of this box. And in 100 dimension this becomes 9. So this still has side length 4, but this ball leaves the box, which is very counterintuitive. So one can think of it's kind of a spooky, a spiky things, high dimensional spheres that protrudes these regions. But our general intuitions fail in higher dimension. Another example is this. Let's say I have one square which has side length 2 and I have a unit ball placed in it. How much percentage of the volume is occupied by this ball? In 2 dimension, if you do the calculations here, it's 78% of the ball. 78% of the square is occupied by the ball, which is a lot of area. But then if you go to 100, and the value decreases. In 10 dimension already it is from 0.78, it's just 0.002. And 100 dimension becomes 10 to the power minus 70. So it's, in that case, even if you say trillions and trillions of points are random from the interior of the cube, you will almost never hit the sphere, which is very counterintuitive again. Let me give another last example. That let's say I give you a particular orange, let's say. We are given an orange. So when we give an orange, what we do is we peel the orange and eat the inner portion, and the peeling portion is this orange portion. So let's say R is the radius of the orange and T is the thickness of the shell. Then what fraction of the volume of n ball of radius R is contained in the shell of radius R and thickness T? So this is the calculation, you will realize this number is this value. So if you go for dimension 500, let's say, then you will realize that 99% of the volume is contained in the shell only, which has only 1% of the radius. So message from this is, if you are peeling a high dimensional orange, probably you should not, because if you peel a high dimensional orange, there is almost nothing left. All the orange's mass is in the peel itself. Let me conclude with all this works which is done by my students, and this is my new YouTube channel about algorithms, algorithm. So if you want to know about algorithms in more detail, for example about the stable matching problem I mentioned, or about the connection of Sanskrit prosody and dynamic programming, you can go to the channel. And this is my lab, SEO lab, and these are my students, and this picture actually has 20 meta references to theory CS. For example, this is fox, this is soda, this is sausage. They are names of some conferences. There are many more. So this is multi-amp bandits, which you might like that. And some of them are my master students, Eklavya, KVN and Aditya. They are doing PhD now at IISc, Georgia Tech or UIUC. And the students, they are Google PhD fellows and other awardees. So let me conclude with CSA is the best, and this is acclaimed by all these legends. Can anyone guess who are these people? Who is this? Is Euclid or Pythagoras, one of them. This is Aryabhatta, this is Al-Khwarizmi. This is Fermat, who gave first probability kind of the rigorous treatment, Turing, and this is Kanut. Thank you.
Now I would like to call Rishi on stage to present a token of gratitude from the database community to Professor Arindam Khan for sharing with us his expertise and being a constant support during the filming of today's event. Next, we have with us one of the foremost voices in artificial intelligence and machine learning at IISc, Professor Chiranjeev Bhattacharya of the Department of Computer Science and Automation. Today he will be sharing insights under the broad theme of explainability, model surgery, and quantum EM, which nets in machine learning. So without further ado, please join me in welcoming Professor Chiranjeev Bhattacharya as he guides us through his exploration of ideas at the forefront of machine learning. Welcome, Professor.
Thank you very much. Will you be able to play that? Just to switch the slides. I just. Yeah. But what is happening? Is talking to some other machine?
No, this is only for HDMI.
HDMI, right?
Converter we can use. Either here.
This I will try. No? Finally. So good afternoon, all of you. So I must say the last talk was a little disappointing. He got a fantastic talk, but no questions. So do you want to ask him some questions also, or no? What is the format?
You can ask anytime.
Anytime, but not now. I was thinking, no, you just had the talk because they didn't allow you to ask questions. Okay, yeah, but it was excellent talk what he gave, right? Okay, so now, so I was thinking that I was not sure what to present. So thinking what research we are doing, we'll try to tell you some of those things. Yeah. So explainability, model surgery, quantum EM. If any of you are feeling lost, it's perfectly fine. I'm going to explain what that means. Okay? Just stay awake. We'll try. Okay? So the first thing is, of course, this. We are living in the age of AI, in the era of AI, and especially your generation has a huge opportunity and a challenge as well. So it's one thing to say AI will change our lives. We see newspapers and all that, right? But some people don't believe in that. It's just somebody said something. Same happened to me also. Do I do research? My research is academic in nature. So one of the things that hit me when we were doing this project during COVID times. In COVID times, all of us, in our own ways, try to do. I'm sure you must have also done something, whatever way to help at that difficult time. So at that point, some of us, me and some of my students and other colleagues, especially from Art Park. Art Park is a company out of IISc. Niramai is a startup company in Bangalore. So we got together and thought, what can we do? So we built this thing called X-ray Setu. Setu means a bridge. X-ray is, So to illustrate this problem, I will show you a video on that's best after lunch. So in other words, it's just an app, right? And after that, let me play the video. Then we'll talk to some problems we'll see. As of now, though it's a little old now, but it's their DST website. Extremely proud of this recognition. So now let me, oops. There we go. Yeah. Now, after lunch,
65% of the 1.3 billion population lives in rural areas. Rural India has only one radiologist for every million Indians. COVID-19 has rattled our health infrastructure like never before. RT-PCR tests are often delayed in rural India. X-rays can be a faster way to identify COVID and plan early intervention. Introducing X-Ray Setu, quick chest X-ray interpretation for doctors via WhatsApp. Developed by the AI researchers from Art Park, Niramai Health and IISc. X-Ray Setu, bridging the gap between accessibility and technology. How does it work? Step 1. A doctor clicks the picture of X-ray image using her or his mobile phone. Step 2. The doctor then shares this picture on WhatsApp with X-Ray Setu at 804-616-3838. Step 3. X-Ray Setu AI service automatically generates a provisional report within minutes. Step 4. The generated report has probability of COVID, pneumonia, markings on the lung image, and markers to other abnormalities. The doctor gets the report within minutes on WhatsApp. X-Ray Setu helps our COVID warriors in their fight against COVID. Key highlights. 300 plus doctors have trusted X-Ray Setu over the last 10 months. X-Ray Setu is accessible and easy to use. No apps to download. It works with both analog and digital X-ray machines. It also works on low-resolution images. It marks 15 lung abnormalities, including COVID. The best protection is early detection. Here is what doctors say about X-Ray Setu.
Let's get back to the presentation. Hopefully that give you an idea about the thing which we did. So this was built out of this department, few students, stuff like that, right? We are just blown away by the reception it got. This is one of the good days, in the sense we got hits from across the country. So sitting in a room here, at that point of course in our homes, few students do something, and people around the country, are downloading things, using it, giving us information. So if you realize, the product was built for whom? It's not necessarily for a city. We have a lot of good hospitals here and all that, right? It's for rural India, where there are not enough doctors. The number of radiographers are more, radiologists are very few. And this exactly touched the heartland of India, because we know where they're coming from, rural cities, rural places. So first time, just, I was really humbled by seeing this. So now that took me, okay, how should I, then this should, and I'm quite convinced, this would be the next generation of healthcare. Tomorrow's hospitals will look very different. And of course, you see some of the things already in play. So one of the things is, this is an example what we call as M-Health, M for mobile. CII, for example, in the last few years ago, is all taking notice of this. This will, so they are calling out that this will be one of the vectors on which healthcare will revolutionize, right? But now, so this sets it, okay, useful technology, we can build things, we can deploy it. So how to develop this further? Is it a good technology, first of all? So for example, here, what are you doing? Are looking at X-ray and deciding you have COVID or not. That was the problem. Now, machine is giving you some decision, right? Can I trust it? Is it reliable? How do you answer these questions? Only then I can deploy it in such critical situations, right? And now, so this is one question, and I'll try to demonstrate to you it is not that trustworthy. You need more science technology to be built. And the idea is to share this with you is not so much what we have done, but this is the questions we want to think about, and I'm sure your generation will be challenged by these kind of questions going forward. So keeping that question aside now you see, but it was useful by and large, right? So why was it useful? Like, what was the power? What is the magic? Why could it do taking X-ray image and giving a decision very quickly? The magic is in the so-called deep networks. Some things you put together, deep networks. So a brief history of deep network. We started in like 1950s somewhere in labs in MIT and all that.
At that point, they could barely train like 10 neurons and things like that, right? Today, 2025, I'm sure, I don't know the numbers, but probably 100 trillion parameters are there, models are there, I think. So one sobering thought. Now these things all been said, okay, because it mimics the human brain. Now if we say neural connections are like the quote unquote analog for the our neural network parameters, a sobering thought is like a human brain has 100 billion connections, far lesser, and yet can do many things, right? So this is okay, this is good, but so let's do, but this power has helped us build many things, right? So one of the things is like ChatGPT. All of us who use it. How many of you use ChatGPT? Wow. Any other competing product? Gemini. How many use Gemini? Oh, ChatGPT, Gemini, very good. Any other product? I don't know. I know these two. Claude. Claude is how? Claude is also, everybody uses Claude? Claude? Okay, only one. Okay, good. I think this company should be here. Good for advertisement. Okay, so because I know only this, So let me ask. So what do you do to ChatGPT? You ask.
I have to ask that.
Now I know. Students say somebody so good assignments. Why? Now I know. Not they are smart, but they're getting help. So, okay. So you basically ask questions, give me answers back, right? All right. So now things which we have built now, that's the same thing, right? You're gonna supply to ChatGPT. Those are built pre-LLM days. Anyway, now I ask the following question. What is ChatGPT? In a nutshell, this is basically some deep neural network model. Then ask this question, right? GPT-4, you know, right? ChatGPT is a little advanced version of that. So what's the electricity cost of training GPT-4? Yeah. That number of gigawatts, it's a number, right? It can power a city like Bangalore. So this power is coming at a price. Now we have decided, and it's important, that AI is going to affect our lives. But is this sustainable? These are things you should keep in mind, and this will help you. Then opportunities will come, arise how to solve this problem. That's what I'm sharing these things with you. Okay. So now, the long story short, because of this large number of parameters to training and all that, it's now one of the ramifications is you see huge amount of electric power. Okay. Now, so have you used this? You know what that is? Okay. I just saw this news. So Perplexity is that Indian CEO now, but I don't know he's Indian anymore. But the company is doing very well. No, he's still an Indian passport?
Yes.
Okay, good. Anyway, so that's the thing, but US is amazing things is doing, right? This is one of those browsers. What does the browser do? Those of you know. So the thing is that Google browser is there, no? So why should I use this?
It uses the AI person.
Yes, a US browser. So now, this is not just they can do, but this is not catching up. See, 21st October, this week. Now Google already has a Project Mariner. Why? Companies, by the way. So, what's happening? So, future of search. 2000, internet started. Today's world is now you are CS engineers, right? Where the maximum of jobs go? Maximum jobs is essentially around search. Google, Microsoft, Amazon, all are search. Now the future of search is this AI-powered browsers. Right? Now if you have noticed this, I was noticing them playing with ChatGPT. Okay, I only have the ChatGPT, that too not often, but at least like 3-4 months ago also I did not see YouTube feeds showing up in my ChatGPT thing. But now I see YouTube things are also showing up. Right? And those of you who do not know, try this SEO, search engine optimization. Now there's a whole industry where CS graduates are employed and things, and how to, somebody has a query in Google browser, and you are selling something, and obviously, okay, we want information, right? But the main economic driving force is advertisement and making buy things, sell things, which we all want, right? Now, how do I surface my company's products at the highest? So therefore, optimize for that particular search engine. Now, these things are completely open, and that is the new, in my opinion, a new opportunity slash, I would say, challenge as well. Design algorithms and things like that. So I search a query in ChatGPT, some product comes up. And this is the so-called agentic LLMs and things like that. The names goes by these things. Of course, the point is that okay, we haven't done any of these things, but this is to show you this. If this is the future, now what is the price for the future? Okay. Now here is quotes from a very famous person. So you know this person? Okay. Look up this name. So now Google search and do this figure, right? Take a picture and find out who this person is. John Hennessy. He is the chairman of the ABC, the company. He's also a very famous computer scientist. And look at what he says. An exchange with AI known as a large language model will cost 10 times more than a standard keyword search. Now, hopefully you got the point now. When I write in Google, I'm doing a keyword search. Now, when you will interact with Comet or the ChatGPT Atlas and all that, you will interact with the AI model. It's going to be 10 times more expensive. And that's his claim. Anyway, but that's the idea that it's only going to be expensive. Why? Why do you think it's going to be expensive?
The AI model should run.
So where is the expense coming from?
Analyzing different pages at once.
No, what is the expense? What is so expensive about it? If it's expensive, then it's not going to. Then it's not got a good model anyway.
So many parameters.
And that causes. So where is the price I pay? Electricity. Every time your GPU is gone. So that is now, Mr. Wang says 80 to 90% of the cost machine learning is AI inference. What is AI inference now? I type in a ChatGPT question, answer comes. That's inference. Training is one thing. ChatGPT answer training. This is inference. Every time you now ask a query, you're coming back, right? Now how do you solve these problems? This is now, I would say, industrial problem. Hopefully I give you that view. And now these kind of problems are dominating today's industry, and that's the challenges you have to rise. Young people like you should be able to solve this problem. So that is the generational challenge, I would say. In other words, just to belabor the same point, I would definitely recommend all of you to read this. So especially, that's the future, is amazing, it brings new things, but what is the cost? Again, one of the ways to propose this cost is to look at the carbon footprint of DNN models. What is DNN? Deep neural network. I'm just saying it, right? Carbon footprint. Okay. Let's see what I mean by that. So this is like a dated paper. Okay. So what are these things? These are standard models. It's a little dated though. Nobody uses this anymore. Okay. Now more powerful models have been built, right? So apparently these numbers are we just will not focus on the last number. We'll just focus on these two columns. These are energy consumption numbers after one iteration of updating its parameters. One iteration. So every time you train a model, right? One iteration. Okay. How do you measure the energy consumption? See, for example, those of you who are started training these GPU things, you will see if the GPU is there, your room suddenly gets hotter. Electricity is burning. Okay. So these are numbers pointer, right? So any number needs some context. So now you see this number is this, right? And now this is for example, in United States, you have available this ratio of how much of this electrical energy came from coal, how much of it came from hydropower and things like that. So it came from coal. I will say this is the carbon dioxide equivalent, CO2e. CO2e is carbon dioxide equivalent. Okay, so that means if it's this is this, whatever. And now for India also some things are there. You can say, right? But to this kind of things, so okay, how do you interpret this number? High, low, how do I know? Let's see, get some context around. So now you see so one passenger, New York to San Francisco, if you go, that is the CO2 equivalent, 1984. What is the number here? 1438, one iteration. And you take any NLP conference, of course, nobody, now there are more powerful models than BERT, they would run many iterations to get to that number. Okay. Now, what is more alarming is this transformer models. Now you have more fancy transformers. See, it has something like this, 6 to 6, right? And what is that? 1 to 6, 5 times. Now, whole world is now sold with the idea that we need AI models. And of course, it's such a powerful technology, it will change our lives. But is this sustainable now? Then how do we solve this problem? So you may want to read more about this paper. I think it's a very important paper to read. And of course, when the paper came out, a lot of criticism happened. Is numbers on right and all that. Agree, the numbers may not be the best possible, but I think the main point is that the power of AI comes from over parameterization, large amount of data, but it has a huge carbon footprint, which makes it completely unsustainable. Because everybody wants to build their AI models. So this is a challenge you all collectively have to solve, and especially your generation. And for that, you should train yourself better if you feel like this, right? Whatever that means, right? So here we're going to present some of our other research. And now, here's also another interesting news I wanted to show you. Right? So Scarlett Johansson is one of my favorite actresses. Maybe many of you have seen her movies. So you can track this news. So it says that some of the OpenAI models, they also have voice thing, right? And many other things can be seen as if her voice. A, she didn't give permission. B, her voice is also fine. You can say it's synthetic, but many people may misunderstand that she may be saying those things. And why did that happen? Because when models were built, you scrape all the data harvest all the data from the internet, scrape it, train it. Now it's one thing to do for research, another thing to make money and say people can misinterpret. And these kind of lawsuits are going to happen more often now because most of the models are built like this.
In India also it happened. Anil Kapoor did something.
Yeah, so I'm saying this is coming now, and you will see that a huge amount of lawsuits are going to come. So the challenge now is to ask that, okay, now the thing is that, okay, now I say that no, you are misrepresenting me. You should not use any of my data. So what is the thing I should do now? Should I now? But one thing is that I can't live without the model. All of us are using it for assignments. So what should I do? So now one thing is that, okay, fine. So you take the initial data set, remove the person's information, retrain. Possible? 68 gigabytes. So what should I do? So this is creating new challenges. This is something called machine learning. And this is one of the things that we like to forget. So how do you solve these problems? These are interesting open problems, and these have immediate consequences, right? Okay. So that being the pitch of problems, and how much time do I have? Just to gauge myself, maybe another 15 minutes. 20 minutes. So, okay. So now this is basically we talked about various problems. One is that for X-rays the quote unquote is it reliable and things like that. Another thing is that the models need to be it takes too much power, right? And also we also motivated something like that there are challenges now that you may have to unlearn a few things. So this all comes under the big theme of responsible AI. Okay. So we have been doing some work on this, and that I'm going to present in the next few slides. Our own efforts in this direction, very preliminary, of course. But more importantly, it doesn't matter what we do, but what I would like you to ponder over the questions I posed, and you should reshape it in your own way. Okay. So the agenda of the remaining time would be something like this. First, we'll talk about the explainability, then model surgery. So what is surgery now? So I'm calling it surgery. Why surgery? Yes, I got a model now, because I am not allowed, I don't want to retrain from scratch. So then what can I change? I'm calling it surgery, right? So one of the things is pruning. What does pruning mean? Oh, that means you said, it takes more electric power. Why? Oh, because there are too many parameters. Remove a few. Pruning. Unlearning. Change something. That's all I can do, right? So I'm calling it model surgery, by the way, right? This is a coinage we came up with, so nothing fancy. And if time permits, we are going to talk about something to the quantum, the advent of quantum computers, right? So quantum EM algorithm thing, but I don't think we'll get time for that. But well, let's see. So now let's come back to explainability. So we wanted to understand chest X-rays for that matter, but I think it illustrates more points than just simple chest X-rays, and all thanks to our X-ray Setu project, right? So in essentially, if you look at X-ray Setu, what is it? So basically, it takes in a chest X-rays, and that is the big rectangle, right, Arindam? No. So not squares. So that's basically a deep neural network. Nothing like this. Some way it's some standard network we borrowed at that point when we did it, right? And it outputs you predictions and annotations as same, right? And it does this 15 annotations, right? Okay, so that it does. Fine. It also generates a report like this. Now, okay, 2 years ago I shown this, everybody said wow, but now I said, oh, LLM can do it, right? So this is pre-LLM days, but I can see the technologies are already there. So it has to mark out a report for you, just like, so basically what is trying to mimic? It's to mimic a radiologist. Radiographer takes a picture that you go and walk into. So basically, just to get to the feeling, if anywhere you go, X-ray taken 10 minutes. Report, no, come tomorrow. Why? The expert has to sign that. This is the thing. Of course, so this is possible now. And the thing is, you have to show these markings. Why? Why do you have to show the mark? So I just say you have COVID. Huh?
We need to justify the outcomes.
This is the first time we saw that problem, actually. The first time I said that I just can't go and say you have COVID, you have pneumonia, because there's consequences. Then you have to test and all that. I just say, oh no, you'll die in a few days. As good as that. So, but the AI technology which we use have been matured in a very different regime. What is it? Oh, I want to buy some books. I want to buy some shirts. I want to see which movie, Netflix. But there nobody asks why. Some movie, if you get it wrong, who cares? I mean, heaven will not fall, right? But this creates this thing. So that means it's not that we wanted it, but we are forced to do, which is a good thing. So that's why the marking. So now we'll talk more about this. So how do you do this now? So the point about this kind of technology is this, that you not only have to tell me a decision, you have to tell me which part, if it was an image, which part of the image was responsible for your decision. Okay, and that's the, and so we could, for example, you got a few images annotated by radiologist, and the machine, we did something, machine can actually figure out the same region by and large. Okay, so now since looking at the importance of it, as I said, we are intrigued and we studied, this can be the cartoon of that X-ray Setu model, right? And our focus mainly was on that thing which is built on called AI, right? That's where the deep network and the box was, right? So that's where we want to focus attention on, right? So now if you realize the setting is as follows, no? There is original X-ray, and what do? You take out your phone, just point your camera, scan it, send it through WhatsApp. Fine. Now in many cases, when you look at the two X-rays, to untrained human eye, you'll see hardly a difference. But the machine sees a lot of difference. The red colored things are the machine's difference. Right? It's red. Red is a number mark, but it's a difference. But to the human eye, it's by and large. So does it have an effect? Okay. To understand that, what we did was at that point, right? So these are names of some networks during COVID time. No, groups around the world. They are trying to help in their own ways, right? So there are many networks available. These are just only few of them, very popular ones. There are other networks also. So they also predicted COVID and things like that. So these are names of them. So I did a simple experiment. And these are all trained on what? Original X-ray images. We just take the original image and I take the WhatsApp image. Passed it to the same model. What should the answer should be? Same. There is a fraction of them, they are not same. Now this is a fraction of images where the predictions were roughly not the same, right? That is, if there are 100 images, the first number says at least 7% of the images, the values were different. You will say 7% fine. Was it fine? For buying books, it's fine. Okay, if I recommend a horror movie instead of a romantic movie, it's fine. But not for this. You see? So this is one of these problems. Right? So it's called prediction instability.
So disagreement, false positive and false negative, or like what does it mean?
No, disagreement means the original model, when I pass it the original image, it is saying COVID. What I now do is I take a same image, WhatsApp image, it is saying something else.
But it's not COVID, is not labeled as COVID.
It could be, yes. Both ways. Both ways. See, no, what I want to do the following is not about that. But that whatever the original machine says, it should be the same thing. Right? Because it's consequential. Right? Okay. So now, as you see, so basically these things are not studied at all. We are the first ones who tried to make a study about this thing. Right? Okay. So after lunch, study formulas. But anyway, this goes in basically the measure which I showed in the last thing. Right? So the idea is to measure. So you take origin, X is the image, M is the model, and what is R of X? R of X is that you pass it through WhatsApp. Okay? Then R of X. Now, Y is the prediction of the model. Now, how many? They should be same. That's what but it's not same. And to catch that is a measure we came up with, right? Now, the point is that you have to think, why are we breaking your head? Why is it? Those of you who have trained deep networks, okay, you take some of the WhatsApp images and train it, no? Put it on trade dress and it's fine, right? Now, the question is what you want to do is, now if you want to do M-health, M-health is what now? That each of us should build our own models. Why should it be tied to a particular implementation? I should build my own apps. So that is why we kept the thing that you're not allowed, because you don't know which app you're going to use. Anybody should be able to use it, right? So that means my model will be trained only on the original image. And I cannot in my mind imagine all possible permutations. Somebody use WhatsApp, somebody use something else. For example, government a few years ago, some of you may have it, called Arogya Setu. There was one app. Didn't pick up, that's fine, but at some point we'll integrate this into the Arogya Setu app, right? But people may want new apps. So that's why that's why this problem becomes more important. So this is called prediction instability problem, and you saw some of the values when empirically measured in last, right? Now the second thing is explainability, right? As I said, just to help you explain the technology, like let's assume there's technology available now. For example, now there are now powerful image recognition algorithms. For example, this image, somebody is brushing the teeth, right? That label comes up. You said, why did you say brushing the teeth? So now technology is available to you, so that's something happening in the red colored place. This technology available because I said brushing teeth because something happened in the red colored region. Okay, there is something cutting trees. Okay, this is the cutting trees, red colored region. Now you look at the red colored region and you agree or disagree, whatever you want. So that goes in the name of explainability when computer vision goes. So this technology is available. So you can bring the same technology to our X-ray Setu project, right? So basically, these are called class activation maps. So basically, the same technology can be used. So you take your X-ray, pass it on, and suppose in the last layer, where a bulb shines up, COVID-19. Now you can mark it using those class activation maps. These parts were responsible for your lungs. That's the technology, right? Now, because of deep networks, lots of parameters. For example, so forget at this point we are saying just forget even WhatsApp. Let us take original images, right? So the first thing is there's no COVID. First image, COVID-19 minus, right? No COVID. The prediction is correct. Machine is predicted correctly. But if I quiz the machine, why did you say so? Where is it pointing to? Outside the lungs. The black arrow. The black arrow is, I'm trying to get you the thing. The black arrow, this is the thing. So prediction is correct, but I quiz you, why did you say so? You're pointing a place outside the lungs. Of course, we agree that the class acquisition map technology is not perfect, but it's a good approximation. Now, would I believe it now? So this is like the challenge, right? How do you solve these problems now, right? And of course, the long story short is again, sorry for the math equation, but again, the way to measure these things, like outside the lungs and all. So now again, you do a similar experiment. You take the original, the 10 networks, you ask the explainability of it using the measure we just flashed one slide back. higher the worse. So the grey colored thing was original image. Explainability anyway is not great, but there are lots of concerns here, right? After WhatsApp, it often makes it worse, slightly. So now, how do you solve this kind of issues is one of the things, right? Okay, so maybe we want to do other things, so I'll just quickly say what we did. So there is something called multitask learning. Well, it is more like a heuristic. So basically, your task can be, you can find all kinds of other information, infiltration, effusion, this and that. These are all different kinds of lung abnormalities, and then you tweak the objective slightly, differently, and this reduces both the instability problem and the, multitask learning and the explainability problem slightly though. But in my opinion, okay, why this we did, this is far from answer. A lot more high quality research needs to go in, and this kind of, the way I'm pointing it, you usually can do the experiment yourself to convince yourself that this is indeed there's an issue, right? Okay, and if I want to read more about this is their paper. We have done more developments. You can find more in our website. This is a little old paper which has some of these discussions. Okay, but now let's move on to the model surgery issue, right? So now, as we said, surgery is this is a different theme now. Editing and unlearning is what we're calling it model surgery. We defined it. So this is a bunch of our students, Dhruva, Chaitanya, and Tanay. So now, like it's based on 3 papers. This is a couple of ICLR papers, and I think they went to Africa, had a great time. So and then so these are based on these 3 papers, results are. So, but here is one slide though on model editing. Though I motivated through Scarlett Johansson, right? But there is more at play here. For example, there is this very important legislation coming out of EU, and all the companies here are very worried about this. It's called GDPR, General Data Protection. And one of the things is that right to be forgotten, right? That if somebody says nowhere in your algorithm decision making you should use my information, it's a right. It's not something which which is like, oh, it is good to have, nothing like that. It's right. It's a law. So now, how do you comply your algorithms to that? So this for right to be forgotten. And one of the things that I said, that one instance of it. So this kind of thing ties into that kind of issue, right? So now, keeping all those motivations aside, so what is model editing now? As we said, I see. So you have a model, somebody has trained all that. Now you want to change it. You want to make it smaller, or you want to, edit some parts of it. But the question is, how many parameters you saw? 100 trillion. Which parameters? Which one should I throw away? Right? So identifying them. That is the technical question boils down to that issue. Which one? Right? So now, of course, we are not the first ones. This is a huge amount of work going on across the globe. So I can imagine that. So existing work, what I saw was that they'll say that unlearning part is pretty new, but this pruning part has been going on quite a bit, like 4 or 5 years now. So the standard formulation is as follows: you take a model from the internet, whatever you wish, then say I'm going to change. I have to find out things which I want to remove, but I will need access to the original data set and how did you train, in the sense that what loss function did you use. So why so? Because then I will be able to guess. Because your gradients and all that, those are to understand gradients. So the gradients were this. I see. So this is not a rectangular gradient, so this is fine. Let's throw them away. This kind of decision making is going on. Okay. Now it was triggered by conversation which I had with some local startup companies and people here. So this is see, we only can get the model. Model like Hugging Face, I go and get the model. And often this kind of model nobody gives the data set. Now how do I guess that? Nobody tells me how to train. Even if I train, I won't have that kind of power also. So that is the point we pick up from. Okay, so what do I have? model. And what else? And also you know what you want. I want cats and dogs. I don't want cats and dogs and trees. Trees I don't forget. Cats and dogs all I want. I know this information, right? So that's the setting. So can you do unlearning and pruning in that setup, right? Okay, so let's take the pruning to illustrate this. So first, since I do not have the original data, and original, how do you train? I don't have that information. Okay. But I have the model, I can do as many experiments I want. So the question, I also know, I have also know that I have to do good only on cats and dogs, right? Now to that end, so what should I throw away? So now there is a more refined version of this throwing away. So one is called structured pruning and unstructured pruning. So please don't take read too much into this way we have drawn this cartoon. These are basically units of a deep network. One of the things is one parameter. That's called unstructured pruning. Now people have said just throwing away one parameter may not be the best way to do that, engineering wise, because what you want to see? Energy is what? Power into time. Okay. Now unless that parameters translate to that, I won't be able to. What time now? Inference time. The time you fire a query, answer one. That's inference time. Now to impact that inference time, if we just randomly start throwing away parameters, I will not be able to engineer it to get the gain. To engineer it, and I have to throw away this block. They're called structured pruning now. So people have said structured pruning probably is the way to go to realize the problem we want to hit. My problem is not to get the model with least number of parameters. The least number of parameters should correspond to lower inference time. Now to engineer that better, structured pruning is the way to go. And what is the structure now? Let's assume group of parameters. Let's not get into it. These are called filters. Okay. So that's why this contour is that, right? Okay. Now here comes our idea that since I do not have since I don't have the original, let's say the loss function, right? So I need to have a guidance on. I don't have the loss, so I need some guidance on which neurons to keep and which to throw away. So here is a simple experiment, or rather an idea. So let's call this as a filter, right? The brown filter and the green filter. Filter is a block. What's the output of the block now? So a bunch of numbers. Okay. Now, question asked was, make sure you realize cats and dogs well. So what I do is I don't have the data, original data. So I go and shoot some images of cats and dogs, not the original data. Pass it through the networks. Look at the filter output. Right now, in the brown colored filter, you see the images. So if I just plot, let's assume there's only one number coming out, so that the plot becomes easier. What happens? They have histogram the plots, or rather not histogram the actual values. If you plot, there are sort of use the browns and the greens. Browns and the blues, right? Now, which one should I keep? Brown means dog, blue means cat, right? Which one should I keep? You see, from the output, I am unable to make out it is reacting to the cat or dog. Whereas from that output, I can make out this, right? Right? So that is the idea. So which number should I measure now? But let's so you got that top one, right? But the question is, what do I measure now? It's not one cat or one dog. It's a reaction to the distribution. Yeah? That the output of the distribution of cats, many cats and many dogs, right? Which cat? So I just can't have one number to go with. So here's a technical challenge now. That is now, how does this react to this distribution of cats and distribution of dogs, right? And that is this probably that. So that means I need to have a way to measure the difference between the output of a filter between the two distributions. What are the two distributions? Cat and the dogs. Right? And now I don't have this training set, right? And now we go and shoot, as I said, shoot some pictures and try to now come up with measures. So what is a good measure now? So those of you who know a little bit of statistics, so it's something. TV is for television, no? total variation distance. So this is a notion of a fancy distance between two distributions, right? This is one of the more relevant distributions. You can use other distributions as well, but this is probably, so now you see, I'm called upon to measure the difference between the two distributions. I'm sharing this. These are things you should build your competence on if it's new for you. Okay. So now we went with TV distance, right? But TV distance is easy to state, which I'll not do after lunch. Bad idea. Maybe in the morning could have done this. Well, not state it, but let's say it's a measure formula given to you, which says okay, how different are the two distributions. But then is one thing to write a definition, another thing to compute it. Okay, so computation is reasonably hard, right? Especially in this setup. It's more or less often intractable. But as usual, whenever I see distribution, first thing you should do is, for a special case, is it easy? Yes. Or not too easy, but if it is Gaussian, I can get reasonable estimates. So that's what we did now. So this Hellinger is a way of measuring under distance measure, and we can use a Hellinger lower bound on the TV distance. And the idea is that these are, so now if dA, so let's assume these are two Gaussian distributions with the mean with the mean vector mu1, and sigma A is the it's like, assume the Gaussian is spherical, that is it is uncorrelated, and all the diagonal entries are sigma A. So the economized formula comes out. Okay. Today my goal is not to understand TV distance that well. That's not my goal. My goal is to quickly identify which neurons are acting discriminatively, right? So this was their first attempt. I think it went, right. So now we can use this measure, and now just to finish the thing now. So basically now I have k classes. What should I do now? Then I have say cats, dogs, monkeys, etc. So take all pairwise differences, right, and say which of the things has the least or the maximum separation, right? We call mean TVS distance. Put some threshold and things like that. And so I'll just click this. So you can come up with an algorithm like this, right? Ignore the second slide, second point. That is something we did extra to say that how easy is to prune a layer or not. So basically you can use mean TVS scores, and how that, as I said, through Hellinger distance and all that, you can do all that scores. And now let's see. Here is one proof of the pudding, right? So TVS prune is our algorithm. So TVS name is clear, right? TV distance, pruning is the pudding thing, right? Now these are all state-of-the-art baselines, especially the second one, chip. Chip is again pretty powerful baseline. All of them require access to the training set. I don't have the training set. I don't have the loss function. And what is very, very interesting to note is the blue line is ours now. Now as you can see that let's say on one data set, no, roughly 20% of the things you can easily throw away with no loss in accuracy. Based on things you know, is it a bug or is it a thing or is it even possible? Those of you who played deep neural networks should have, I'm saying, you don't have no theory for this.
It's possible.
Why?
Because when you fix the architecture, many things can do similar work also.
So these are called over-parameterization. Over-parameterization. I have more parameters than I need. And that's the reason you are paying these high prices. Okay? Now this gives you a way now, without having access to distributions, access to actual data, we can still do things and make things lighter, right? Anyway, so this is one line of work. Then, okay, the next obvious thing is that, okay, that you did for Gaussian and all that, right? Now it's not, that looks like assumption, not to push the boundaries for it, but it's not very nice, so I know things are not Gaussian. It's one thing to say it works also, but that still doesn't give us enough thing, right? So now to do that, so what was the thing I was asked to? Oh, TV distance, if it is high preserved. I know TV distance, I also know TV distance is hard to compute. No point even trying. So what can I do? I can put bounds. So which bound should I apply now? Lower bound, right? Why lower bound? because you want to say this number is high information. If I can prove a lower bound and that is high information, same information, right? So now our goal is that if we put a different goal now, can you compute lower bounds on TV distance? And what did the, if one is a Gaussian, what is the, what goes into the formula in the Gaussian? Only the mean and the variance, right? It's about second order statistics. That means now, that's all information using, right? So can you compute lower bounds on TV distance? So it's a technical problem, right? And ideas should reasonably robust. So these things are not, these things I can't borrow from any science. This is how to invent things here, right? Of course, now here is a theorem, again, a bad idea to show after lunch. Anyway, so theorems and all that are there, you know, so, I'm sorry, I'm just doing this. So we could derive theorems which are, you know, are interesting in their own right, you know, nothing to do with basically AI or anything else. This has applications going beyond our pruning and papers and all that. Yeah. So since I'm just now again, let's come to the experiments now. So so we called it witness functions. Is basically we said that, you know, you think about functions of the random variables of interest, and then we should be able to come up with bounds on the TV distance using the first two moments. And as usual, since I am here telling you all of this, is that we do better, but not too great compared to TVS prune. But what does it fix? Numerically, you can use TVS prune also. But what does it fix? It fixes that idea that I don't need Gaussianity. Okay. See, it's one thing to have something working, but if you assume something and I know assumption is not right, that also something's wrong, right? This fixes that too. Anyway, but it helps us identify what are called as discriminative components. Now there's one more slide on this. So, so this slide is basically on unlearning, and this will be my last slide. So what is unlearning problem here? So let us say so let's say suppose I want to forget Scarlett Johansson. Let's say I want to forget class 0. So there are digits here 0 to 9. I want to forget class 0. So class 0's accuracy is written in the blue thing. Red thing is the remaining class accuracy. So what's the unlearning problem now? The other things fixed. And what should I do? What is the best way to do that? Throw away all the other things. No. But that's not allowed. Given a model, do changes. Small changes. Right? Now, as you can see, but you can use the idea of discriminative filters, the filters which are reacting discriminatively, right? You know, and then you see now, if you do that, the results are for you to see here. So the blue becomes yellow. Yellow is almost 0, right? But the red roughly remains the same, the green one, right? So yeah. So the point about this is that, okay, this is what we are doing, but more importantly, I think these kind of problems is going to determine the future of AI. Not that what we have done is the end thing, far from it. You know, and I hope some of you will contribute to that. Thank you again for listening. Did I take more time or?
Question answer session. Don't miss for him. Any questions?
Yeah. Yeah, please.
How did you train without the training data? Like, how does the discriminatory thing?
Yeah, as I said, right, to identify that, what do I need now? Think again. So the problem was, information was cats and dogs, no? I can shoot some pictures of cats and dogs, right? Fine. And then let's take this now. Let's take this other image. I want to show you the graph to help. So you see, what I can do is, I take the image of cats and dogs, right? The model is with me. I just bombard the model with this. Just, I'm not training, I'm just forward passing. I take the image and pass it to the model. Then I record the output of the filters that I can do. I'm not training by the way. I'm just recording the output of the filters, right? And that gives me enough signal, because the cats are cats. You know, hopefully if I get enough of them, no? So now that information is enough for me to that's why I'm saying, so for example, to throw 20% of the parameter, right? Now after this, if a thing drops here, now to get it back, I may have to do some training at this part, right? But on this part, for example, I don't need anything. So all these drafts you see are no training. But still there are enough signals because of discriminative components. Okay? Right. Yes, please.
So many times the model, the input might be a very general input, which does not show the difference we expect. For example, if I just say generate the image of a cartoon, and it could generate any cartoon, and maybe a specific cartoon is what I would want to avoid. So how would my inputs be driven? How would I put?
In this particular examples is picked nicely. See, we are not talking about very generic LLM case. Here, what you are saying is there are distinct classes available to you. Clear? In this setup, I'm saying. There I know which cartoon to generate, for example. Then there I have that information. Okay. Now this idea of discriminative filters will not. So what does it requires? It requires the conditional distribution. No. What is conditional on what? Yeah. Cats, dogs. Conditioned on the thing that I'm feeding a cat's image. What is the output of the filter? Right. So here I have that information. So what you're asking is, but if I don't have that condition, this methodology will not work. We have been other research agendas in our lab. We are trying to develop things which will go beyond this. But the idea is to catch the conditional distribution should be separate, should be far enough. That is the crux of this algorithm.
So in the chest X-ray, like when we wanted to identify why the model has made its decision, and we in the examples could clearly see that it is pointing towards is outside. But if let's say it's inside, then how do we evaluate if the point it is pointing to is an actual reason, or is it still kind of noise?
So are you saying so let's get the question more clearly. This one, right? Is the question related to this also? Forget chest X-ray. Is it? Can this question be asked for this image also?
Yes, sir. But in this case, it's easier to.
No. Okay, but the question, what is this also? No.
Yes, sir.
So now people have accepted that this is called class activation maps, right? Not that this is the end, but people have accepted this is a more or less robust technology. So we will not question that. So because we want to build some ideas on that, let's assume that this is true. This no means perfect. This also has errors. Maybe that's your question relates to that. But let's assume this is true. Even then, it is not working into that accuracy in our health case. And the real challenge is for health case. What is the real challenge? Real challenge is that I cannot allow even one mistake, and that creates all kinds of problems. Okay. So this is now. So there are now those of you looking for interesting new problems. See, this is for pre-LLM days. Now the same idea. How do I use it on transformers? Those will be for explanation. Need for explanation will remain. And now how do you do that? I don't think there is a very good answer at all. Okay. So if there are no other questions, then maybe thanks again for listening.
Okay.
Thank you, sir. And now we would want to present a token of thanks and gratitude from the database community presented by Palak. A round of applause, please.
Thank you very much. Yes. Thank you very much.
Thank you so much, sir. And now we have a snacks break for 15 minutes, after which we would come back for more student talks. So, snacks is served. Thank you.
Presentations leave like that.
Back to the next set of exciting talks. Before we proceed to introduce the next speakers, I have a few questions. Okay, quick show of hands. How many of you have tried to check or checked the... Okay, a question to the audience, quick show of hands. How many of you have ever tried to check the prices of stocks, or tried to guess how if a particular stock would rise or fall? Anyway. Who's there?
My.
You're first. You're first. Okay, the order was changed.
Yeah, this one.
Okay, a bit of a technical issue there. Sorry. Okay. So, our next talk dives into one of the most paradoxical concepts in computer science: trusting in a trustless world. Imagine a network of participants, each rational, fallible, or even malicious, yet somehow expected to reach agreement. Sounds like politics, right? But it is also the heart of Byzantine contracts, a concept that keeps our digital systems from descending into chaos. In their talk, Trust in a Trustless World, Tales of Byzantine Agreements, Palak, Rishi and Shishir will take us through the landscape of distributed systems where reliability must emerge from uncertainty. So let's welcome Palak, Rishi and Shishir as they unravel how trust, even in absence, can be engineered.
Hello. Yeah, I'm audible. Today, me, Rishi, and Palak are going to talk about Byzantine agreement. In some sense, will just be like we have to agree on something where not everybody wants to act honestly. So for introducing this problem, I'm just going to start the game. A simple game. So basically, in this game, it's called the dilemma of the Byzantine generals, where let's assume we have n generals. Who are basically want to attack the castle here. Yeah, want to attack this castle here. There are n generals. So now they are looking inside the castle, and now they are making their own decision of should they attack it or not. Now, basically, they want to tell everyone their own preference, and everyone basically decides on everyone's preferences what they receive from other generals, that should we go attack or not. Now, the thing is, if you want maximum damage done on the castle, you would like all generals to attack at once. If you two people go attack and the three people don't attack, then that would be a disaster. So what you would need is you want some decision making formula which will given everyone's preference, they will decide if we should attack or not. So what could be one example of this? Maybe if you know if everyone wants to attack or not, what would you decide on? So one example is just take majority of each preference. That if more people want to attack, you attack. Or else if minority wants to attack, you don't attack and retreat. Another example could be you just fix a general one. Let's say this general one. And just do what he says. Doesn't matter what you feel. Just do what. Completely trust him and just do that. This is easy, right? Now, next, the problem comes in the case when there is a general who is a spy for the castle. So basically, he is working for the people in the castle. So his goal is to stop you from winning. So he will try to confuse all of you to make sure that not everyone attacks or not everyone attacks. Few of them attack and few of them retreat so that they can win. So now what would happen? Let's just say here T of them are traitors. Let's just say T of them are traitors and T has to be smaller than N. Right. In this example, we are taking 5 generals and one of them is a traitor. Normally, what you would say is that if you know who the traitor is, you just say just ignore the traitor and just follow with the other 4 people. But the problem here is we don't know who the traitor is, and that is the problem. We don't know who the traitor is, so we don't. Also, one more thing is like we don't know what the traitor will do. So let's just say our winning condition is if n minus t of the generals attack. So the honest people attack. Then we would win. And it's fine if we retreat also. And we just don't want casualties. Let's just take n equal to 5 and t equal to 1. And now we'll assume that 2 generals don't want to attack and 2 generals want to attack. So what happens is whatever the traitor says, that would become the majority. If he was honest at least. That would become the majority. But what the traitor does very smartly is he tells he doesn't want to attack to 2 people and he tells he wants to attack to 2 people. So for the people who he tells he wants to attack, their majority is they want to attack. So they go to attack those 2 people and the other 2 don't attack. So this is a failed attempt. And this will be very disastrous. This is something we really want to avoid. And this will be very disastrous. Right. Something we really want to avoid. So basically, Byzantine agreement is protocol where we communicate and make sure that such thing doesn't happen. Doesn't happen. So yeah, basically, if a general gets responses from all other generals, how can we make sure that all generals take the same decision? Right. Is this fine? Yeah. Is this fine? Yeah. First of all, yeah. This is the property which you want. All honest parties must arrive on the same conclusion, regardless of what everyone feels. Either everyone should attack or no one should attack. This is the first property. But it's obvious, right? You can decide beforehand that everyone just retreats. This will satisfy this. So we need the next thing, validity, which kind of the interplay between these both makes the problem hard. So if all honest parties want to attack, then obviously you want to attack. You can't be like, although all honest parties want to attack, we'll just retreat. That is not useful for us. If all honest parties decide it's good to attack, we attack. So now this is the problem. So mainly the problem will be like, we need to decide on a value, but we need to figure out if all honest parties have the same value. And then maybe we can use that information to decide. In some sense, this is the interplay between these both is what makes Byzantine agreement hard and even interesting problem. The final one is liveliness, where the protocol should terminate. You should not keep communicating and never make a decision. You should finish your decision making. Before we give a protocol for this, I would like to talk about what the adversary model is. So I told T of the parties can be corrupt. So what we'll assume is the T of the parties can team up with each other in however way they like, so that they can fool people. So maybe if there are two corrupt parties, they will try to maybe fool the third party that these both are doing together. They'll plan and try to fool the third party rather than acting individually. They both can communicate, plan and do it. So it's a simple way to tell it is there's a centralized adversary who controls all the corrupted parties. Yeah, corrupted parties can deviate by providing false inputs or colluding, which means that they team up and do something. So this makes it such that the adversary is really strong and he has the view of what the T corrupt party sees at every time. So if whatever T party sees, he has all the views. This basically makes the Byzantine agreement harder. Now Palak is going to give one of the protocol for Byzantine agreement.
Thank you, Shishir. So what we're going to see is that given a situation where you have n generals and you have an adversary who has T corrupted parties, how are we going to reach an agreement? How are we going to be able to satisfy the 3 conditions that Shishir talked about? So this protocol, everybody starts with their own opinion on whether they want to attack or they retreat. The protocol has T+1 phases, and each phase has 2 rounds, and each phase also has a phase king. Now there are T corrupt parties, and you can probably tell that the reason we want T+1 phases is because we want to ensure that there is at least one honest phase king. Okay. Now at the start of every phase, you have a preference bit, and like after you finish one phase, you possibly update that preference bit, and at the end of the t plus 1 phases, you have your final action bit. That preference bit will tell you whether you want to attack or you want to retreat. So at every phase, everybody has their own preference bit, and the round 1 is where you broadcast your preference bit to every other party. So there you assume a secure channel exists between every two parties, and nobody is overhearing these channels. And what each general is going to do is they're going to collect these preference bits, and they're going to note which is the majority, which preference bit has greater than n by 2 frequency, and they're going to also note that frequency in these two variables, majority and the multiplicity of that preference.
Just a clarification, in both the previous so when you are using the broadcasting means they are sending the same bit to all, right?
So if it's an honest party, it will send the same bit to all. But if it's a corrupted party, it can send a different bit to everybody.
I see. So they are not using the broadcast channel; they are using the point-to-point channel for.
Yeah, they're using the individual channels.
Okay.
So in round 2, this is the phase where you analyze the inputs from the previous round and you decide what action to take. Now, if you have a strong majority, it is easy to decide what action to take and update your preference bit accordingly. But if you do not have a strong majority, and we'll discuss what a strong majority is, you will use this is where the phase king comes in. What the phase king does is, in round 2, he will send his majority bit, which had frequency greater than n by 2 from round 1, he will send it to everybody. Now, if it's an honest phase king, he would be sending the same majority bit, but if he is a corrupted phase king, he could be sending different majority bits, which is why we wanted t plus 1 phases, so that at least one phase king is honest, and we'll see how this is required for the conditions to be fulfilled. So this is the condition for a strong majority. If the multiplicity of your majority bit is greater than n by 2 plus t, so now if t parties are corrupted and you get greater than n by 2 plus t votes in one favor, you would know that at least n by 2 parties have been honest. N by 2 honest parties favor that particular decision. So you would, in that case, you will update your preference bit based on your majority. But if that is not the situation, then you are going to take the majority bit of the phase king, who kind of broadcasted his majority bit in the second round, and you will update your preference bit accordingly. So if you do this t plus 1 number of times using different phase kings in each phase, then you get your final preference bit, and this is supposed to satisfy the 3 properties of liveness, consistency, and validity. And Rishi will discuss how that happens.
Okay, so the first condition we're going to see how it's satisfied is liveness. So as Palak mentioned earlier, we have t plus 1 phases with 2 rounds each. So in total you have 2 times t plus 1 number of rounds. So therefore you know that the protocol is going to terminate in these many rounds. So therefore liveness is trivially guaranteed. Now we're going to try to prove the validity property. So in order to prove that this protocol is valid, I'm going to use the help of this lemma or a property, which states that if at the start of any phase, all the honest parties have the same preference bit, then even at the end of the phase, they will still have the same preference. They will not change their bit after the phase. Now, assuming this property is true, can you think of why it's valid? So I'll tell you the answer. So if all the parties started off with the same preference, let's say all the parties wanted to attack in the start of the protocol, then this property ensures that at the end of the first phase, they will still want to attack. And then you just apply it for all the phases, and then at the end of t plus 1 phases, they still want to attack, and this ensures that the validity is granted. Now we'll see why this property is true. The proof is not very trivial. So let's say at the start of a phase k, all the parties have the same preference bit. Now since all of them have the same preference bit, and you know that there are at least n minus t honest parties, so then you can easily set the majority bit for the honest parties as the bit b. Why is that so? Because since t is given to be less than n by 4, which is what this entire protocol is working for, n minus t is given to be, can be greater than 3n by 4, which is obviously greater than n by 2, which allows you to set the majority bit as b. Now when you go to round 2, this 3n by 4 is further greater than n by 2 plus t. So this is enough for a strong majority estimate, and this allows the parties to update their preference using the same bit. They will not go for the king's majority bit, they will use their own majority bit for this. So the king does not even come into the picture. So now you can see that if they all started with the same bit b, they'll end up with the same bit b at the end of a phase. Now we apply this for t plus 1 phases, so their initial preference will be the same as their final preference. So this proves the validity property. So b is retained as the preference bit and therefore validity is 1. Now in order to prove consistency, consistency is that regardless of what their initial preferences are, they should arrive at the same conclusion. So we're going to use this property that says that if you have an honest phase king, then regardless of what their initial preference bits are, at the end of the phase, all the honest parties will have the same preference bit. Now this implies consistency. Why so? Because let's say in the middle of t plus 1 phases, let's say at phase k you have an honest king. This is guaranteed because you have t plus 1 phases. After that phase k, they'll end up with the same preference bit. And now we just proved property 1, that if they start with the same preference bit for the next phase, it will get retained till the end of the protocol, and at the end of the protocol they'll have a same decision at the end. Now why is this property true? Now at the end of the kth phase in the round 2, one of two things happens. So either they get a strong majority which allows them to set their preference bit to their majority, or they use the king's majority bit. Now let's suppose all of the honest parties decide to use the king's majority bit, which is not necessary, but let's just assume that all the parties use the king's majority bit. Now since we have that the phase king is honest, the phase king will send the same bit to every other honest party, and therefore they will set their preference bit to the same bit. And therefore at the end of that phase, all the honest parties will set their preferences to some same bit. But this condition is not necessary that all the honest parties use the king's majority bit. So suppose some honest party Pi decides to use its own majority bit instead of the king's majority bit. Now when will it decide to use its own majority bit? It will decide it if the number of votes it received for its majority bit is greater than n by 2 plus t. Now since we know that at least only at max t parties can be corrupt, so n by 2, at least n by 2 of these votes are from honest parties. Which means if you go to the point of view for any other honest party, let's say pj, it also would have received n by 2 copies of this bit v. Let's say the bit v is the majority bit of this. So any other honest party also receives n by 2 copies of v. Now therefore at the end of round 1, since they received at least n by 2 copies of v, all the majority bits of the honest parties will be set to v. Keep in mind that the king is also honest here, so the king's majority bit is also set to v. Now in round 2, regardless of whether these other honest parties receive a strong majority or not enough for a strong majority, let's say if they receive a strong majority, they'll update their preference using their own majority bit, which is v. Suppose they don't get a strong majority, they'll use the king's majority bit, which is again v. So this ensures that if the phase king is honest, regardless of what their initial preferences were, they'll end up with the same preference. And as I said before, this property implies the validity of implies the consistency of the phase king protocol. So now this protocol, it used the assumption that the number of corrupt parties can be at max 1/4 of the total number of parties. But this is not efficient enough, because as computer scientists we always strive to make the bounds better. So can you come up with a similar protocol that modifies the phase king protocol that allows for up to 1/3 corruptions? So again, this is not so trivial, so Palak will now explain the modified version of this protocol, which allows up to n by 3 corrupt parties.
So we just looked at a protocol that allowed t is less than n by 4 corrupted parties, and we saw the proof for that. We'll see another almost similar protocol which allows for more adversaries up to n by 3. So again you have n generals, at max t corrupted parties, n minus t honest parties. Now you have t plus 1 phases with 3 rounds in each phase, and a distinct phase king for each phase. Again you have t plus 1 phases to ensure that at least one phase king is honest. Never mind. So the first round is again the same thing. There's a secure channel that exists between every two parties, which you cannot wiretap, and they exchange their initial preference bits, and they note down the majority bit and the multiplicity of that bit. Round 2 is different. So if the multiplicity of the majority bit is greater than 2n by 3, right? In that case, you create a proposal. If your multiplicity is less than 2n by 3, you will not, less than equal to 2n by 3, you will not create a proposal. And this proposal would be for that majority bit. And now you will broadcast this proposal. If you have a proposal, you will broadcast this proposal to the other people.
Finite number of times. Now for the validity protocol, validity requirement, we'll again use the same property, which can be proved